Hi everyone, good morning, good afternoon, and good evening. I would like to welcome you to the second session of our virtual software internship organized by the SPE University of Boumerdin Student Chapter. My name is Nabil Awidad, and I'm a master's petroleum engineering student at the University of Boumerdin in Algeria, and I will be your moderator for today's session. Today's session will be the first session of the 1D, 3D geomechanical modeling. Rahul Talreja. Mr. Rahul is a senior geomechanics engineer at Schlumberger, a professional with more than 7 years of experience in upstream oil and gas industry, where he demonstrated an excellent technical contribution in the areas of geomechanical modeling, drilling operations, and reservoir characterization, with an advanced understanding of rock mechanics, geophysics, petrophysics, and geology. Along his career, Mr. Talreja offered technical guidance and trained more than 30 experts on technical studies that would describe earth stresses and mechanical properties for formation, field, or basin. It has more than 50 technical publications in reputed international and Indian national journals and conferences in the area of drilling and geomechanics, as he received various Schlumberger internal technical awards. So before we start, I would like to remind you to keep your microphones muted and to write your only technical questions in the chat box. Mr. Talreja, the mic is definitely yours.
Thank you, Chief. Thank you, Nabil. So how would you like, before going any further, probably I would like to take a suggestion from you all. Like, if there is a query, what do you propose? Do we solve it there and then, or maybe we do a session for, let's say, 1 hour and then talk about the queries? How do you guys want me to proceed?
Can you repeat, sir?
So in case of a query, I see we have more than 30 participants. In case of a query, how do we want to, let's say, resolve that query? Do you want me to stop in between and sort out the queries of the participants, or do we do it at the mid of the session or end of the session?
No, you can start. No, if in case of any query, I will tell you how to.
Okay.
Okay, don't worry.
So let me share my screen. Please confirm me once it is visible.
Yes, we can see the screen, sir.
Okay, perfect. So good morning, good afternoon, everyone. First of all, thank you all for providing me this opportunity. It's always good to interact with the upcoming talent, fresh graduates. It's been a long time since my college days, but it's always good to interact with you all. So, just to introduce you myself, I will give a good introduction. My name is Rahul Talreja. Rahul Talreja. I'm working with Schlumberger since 2013, and I graduated from university in India, where I completed a degree graduation in mining engineering. Sorry. And thereafter, I joined the field of geomechanics, wherein I got involved in different, let's say, problem statements, different solutions. Maybe in the sessions we are going to cover in the coming days, we will try and cover most of the applications. So if any one of you have, let's say, further queries after the sessions, you can surely contact me via LinkedIn. If there is any query, you can feel free to drop me a message, and I will get back to you as soon as possible. All right. So in these sessions, what we intend to do, we intend to let's say talk about geomechanics. I'm certain that geomechanics will be quite new to you. Most of you because this is not a specialization that is taught in college. Most of us, I guess, we do it during our master's program, or maybe when doing a PhD, or maybe because of the own interest. There are a lot of courses in recent times. I guess the most famous one is organized by Stanford University, where Professor Zubak and his associates they teach some applications of geomechanics. But we'll try to keep it quite basic. We'll start with the basic. Uh, Most of the times we'll be dealing with this software as it's a virtual software internship. If there is a major doubt, maybe you can raise your query there and then. We'll try to address it. Uh, you know. All right. So hope you can see my slide, Nabil. Is it visible, right?
Yes, it's clear, sir.
Okay. I'll cover a couple of slides and then I'll straight away move to software.
Okay, thank you.
So let's first understand what is geomechanics and where we can apply, how we can apply, right? Geomechanics is quite important. Geomechanics is quite important, and sorry, uh, and if you talk about the applications of geomechanics, they vary a lot, and you can apply geomechanics from day one when you are into your field. So it's if you ask me when shall we start doing geomechanics in an oil and gas field, so the answer to that question would be it's same as saying when do you start investing. So you have to start investing on day one of your field, then only you can obtain the major gains, right? So the first thing that you do in an oil and gas field is start drilling, right? Whether be it's a wildcat well or an exploratory well, the first thing that you will do is start drilling. So you will drill a well. You will drill a well. So you will drill a well into different sedimentary or igneous or different type of lithofacies. You will drill into different layers of the rock, and you will try to understand where is the hydrocarbon and things like that. But in order to do that, you have to first drill a well to a certain depth, right? That's the primary challenge. And when you want to drill a well, there are certain things that you want to identify. You want to identify the casing points, because you cannot drill a well in one go. You cannot drill 5-6 kilometers in one go. You need to isolate different intervals by utilizing different casings, right? So you need to decide where you have to land your casings. You need to determine the fluid weight, which is called the mud weight, right? You need to decide the weight of the mud that you are going to use in order to lift the cuttings, as well as to avoid any well float event or kick. Excuse me, just give me a minute. Drink some water. So you need to determine the weight of the mud that you are going to use. The other applications are, you might have heard, some incidences in the industry where a blowout has occurred. A blowout is a phenomenon where the fluids inside the formation, hydrocarbons inside the formation, they leak into the wellbore and rise up with a good amount of pressure and catch fire, right? It can lead to safety events. It's a dangerous event that everyone want to avoid. So when you are planning a well, you want to identify intervals where the pressure is excessively higher in the formation. You want to maintain the safety of the wellbore and the people working on the rig site, right? And once you do that, then only you will be able to drill a well, right? So this is what we are talking about, an exploit, maybe a wildcat well where you don't have any data or any well in the area. This is the first well probably in the field, but these are the primary objectives of a first well that you're going to drill in a area, right? Okay, give me a minute. I'll plug it. So am I audible? Still audible? Rahul, am I audible?
Sorry, sir.
Okay. Okay. Please do drop a message when I am not audible, if I lose the voice in between. I will keep the chat section open in my different window.
Yes, I will make sure to
Right,
tell you.
Sorry?
I will make sure to tell you if you
Okay.
you're on.
Okay. So once you are done with your wildcat well, let's say, then you will go into an exploratory stage of the field development, and you will start drilling more wells into the area. But the challenges will still remain the same. You want to identify the landing of the casing points. You want to identify the overpressures, right? And after the exploration stage, you will go into a development stage of the field where you will drill deviated wells. You can see you will start drilling a deviated well. Now you will change the inclination of the well. Now deviated wells have their own challenges, uh, and where the application of geomechanics is immense, because in compared to a vertical well and deviated well, what you can see is the stress from this side, the stress from the stress from, let's say, perpendicular to the screen, and the stress from the top. The three principal stresses, let's say, if I talk about the stress state on the rocks around the wellbore will change in a deviated well in comparison with the vertical well. The things are quite different. We'll try to understand those when we prepare our model. And with the deviation, you are also cutting across different beds at different angles. When you are drilling a vertical well, you saw that the direction of the wellbore is perpendicular to this particular layer, perpendicular to this particular layer. But when you are drilling a deviated well, it is cutting across at a particular angle. So the angle of the attack also matters. We will talk about it, how it matters, but it can lead to certain problems in terms of wellbore instability. Now, wellbore instability is it's a problem. Why is this a problem? Because let's say nowadays you are very well aware that we are into a we are into a time frame where everybody wants to save money. Now, if you encounter wellbore instability or any problem like a stuck pipe, tight pull, there are different drilling events. If you encounter those events, you are going to lose time, and if you are going to lose time, you're going to cost money. Which is, if it's too much, if a well is too much expensive, you're not going to drill, right? And then there won't be any usage. So at the end of the day, it's all about money. We want to save time. We want to avoid any non-productive time that well might encounter. And geomechanics is a domain where you try to understand rock and how it behaves when you are going to create a man-made disturbance, like drilling a wellbore, drilling a deviated trajectory. What are the different changes in the subsurface you are going to create? All right, there are other challenges, like you might have heard of the term loss circulation. That the mud that you are going to use in the wellbore, it leaks into the formation because of certain, let's say, subsurface events. There can be various reasons for loss circulation. We'll try to understand a couple of them at least when we prepare our model. Let's say, so once you are done with your deviated hole, um, and let's say this is your target formation where hydrocarbon is located. Now, the other objective of all the companies is to produce hydrocarbon, right? Now, if the formation is not permeable enough, if the porosity is quite low, I guess you are very well aware that you have to do something called stimulation. You have to do a hydraulic fracturing operation, right? Unless if because the formation permeability is quite low and porosity is quite low, you want to induce secondary porosity by means of creating new fractures in the formation. And for that purpose, you want to do simulation operations, right? You want to perforate and pump a fluid into the formation so as to, let's say, induce secondary porosity. Now, in order to identify suitable zones for simulation, geomechanics is quite important. You cannot just go downhole and do the perforations or pump fluid randomly. You need a science to help you, to guide you, where do you need to place perforations, where do you need to, let's say, how much fluid do you need to pump. There are many things that geomechanics can help you, take decisions. Then there are other applications like, let's say, you might have heard that in an oil and gas sector nowadays, we are also drilling in basement reservoirs. Basements, it can be igneous, metamorphic, sorry. So in such reservoirs, you can understand that there is no porosity. If I talk about a basement reservoir, an igneous rock, is negligible porosity. The only porosity such reservoirs have is because of the fractures, natural fractures present in them. And the only way you can present the product produced from these reservoirs by means of the open fractures. But let's say when you are on the subsurface, you cannot, how do you identify which location will have the highest amount of open fractures? That's where again the application of geomechanics comes in. It will help you to identify intervals where the fractures are open, and it can help you to decide the trajectory of the well, right? There are many other applications too. I mean, we can go on and on. The whole point of this slide is to tell you that the application of geomechanics, it starts from appraisal, the very first well that you are going to drill in the well, and it goes to the abandonment of the field. You might have also heard of the applications like subsidence and compaction of the reservoir. Now, I guess the story of Ekofisk field is quite famous, where with the continuous production from the reservoir, there was significant reduction in the seabed. Now, let's say if you have a rig over here, let me draw something here. So if you have a, let's say, if you have a rig over here, now if you are producing for this particular area, if you keep producing, that is you are taking out the fluid from this particular reservoir, and with time, let's say after 20 years, 30 years, what was happened is this surface, which was like this initially, and it went like this, right? It went down. This is called subsidence. Now, if you have a structure over here, let's say if there is a platform on this particular location, you can understand the amount of damage it might cause, right? So you want to predict such phenomena where the subsurface changes might lead to a phenomena of subsidence. How much changes we are expecting over a period of time? That is something that also you can predict. There are various other applications. Maybe we'll talk about them gradually as we move ahead, because it will be too much information to consume. Any questions on this slide? Are we clear? Are we clear on the applications of geomechanics? Are we clear? You can just drop a yes message. Cool. Any question to this point?
I think everything is clear, sir.
Okay, great.
Okay.
Great. So moving on to the next slide. So this is the, let me check why this is. Okay, no worries. So what is this slide about? This slide is quite intuitive. On the top, you see I'm showing you different stages of the field. You start from exploration, you start with exploration, you go to appraisal, you go to development, exploit the field, and once, let's say, there is depletion, when you take out a lot of fluid from the reservoir, you try to, let's say, keep your production sustained by adopting some enhanced recovery techniques. So these are different stages of the development of a oil and gas field. Now, Geomechanics, as I said, if anybody will ask you when do you start doing geomechanics in the field, you start from day one, right? You start doing it from day one. As soon as you acquire the area, you start the acquisition of the area. You acquire some data like seismic data you acquire in the field. You can start doing geomechanics. Now, in order to do geomechanics study, in order to do a geomechanics study, there are certain tools that you require. There are some certain technologies that you require, right? Because you cannot do, let's say, an extensive interpretation on Excel sheet. The primary reason being in the oil and gas sector, we acquire data which is quite heavy in nature, and Excel sheet might not be able to handle it. It will freeze, and it will, let's say, it will not be that fast. You might resample it and maybe do some you can apply some simple algorithms, but working for multiple wells, if you have multiple wells with you and you want to prepare multiple models, you want to apply a finite element model, you won't be able to do it in an Excel sheet. So you require certain technology, right? You require certain technology, you require certain platforms where you can start doing modeling. Now, in order to do the modeling, you need to understand the science, that is for sure. But you require a technology which can help you to prepare those models. Now, in Schlumberger, we have excellent platforms. The first platform is Techlog. Sorry, the one you can see over here. This symbol is for Techlog. The first platform is Techlog, and the second platform is Petrel. Okay. Now, in the Techlog platform is mainly for wellbore modeling. In Techlog, we do well by well modeling. Our main focus is on a well instead of a field. We can do multiple well modeling in Techlog, but the main focus will be always on the well, right? In Techlog, we'll be focusing on the well. Whereas when we go to a software called Petrel, we will see that there we will talk about the area. We'll talk about the whole basin or whole block in general. These two technologies are interrelated. They talk to each other. Let's say if you want to, let's say, send some data from Techlog to Petrel, or if you want to send some data from Petrel to Techlog, you can do it. They do communicate with each other. So that is not an issue. But you require these two platforms if you want to perform, let's say, 1D as well as 3D modeling. So as we move ahead in these sessions, I will start with Techlog. I'm sure you have a session on Techlog where you are going to be taught different fundamentals of Techlog. But we'll also try to cover some of them which we require for our geomechanics modeling. All right, so we will be using these technologies on a certain data that I have, which I can show it to you, right? It's an open data set. The name of the software is Petrel, P-E-T-R-E-L. Let me share the name. Petrel, Techlog and Petrel. So these are Schlumberger technologies. Let me maybe take you to the platforms. So if you open Schlumberger website, if you go to Schlumberger website, what you can do is, let's say, go to reservoir characterization. Directly, you can maybe type it Schlumberger Petrel. So it will take you to the software technology platforms. So this is Petrel. You can find different. So Petrel is a very well accepted software in oil and gas sector. It is used by almost all the companies. So it's quite handy to learn this particular technology. Let me see if I can remove it quickly. Okay. All right. No, man. None of these softwares are for free. But industries like Schlumberger, we have a tie-up with different institutes. So you might be aware of different industry institute relationships wherein we donate softwares to institutes, provided we have a, let's say, tie-up with them. Then you might find these softwares in your lab. But yeah, these cannot be given for free to all the individuals because they are quite expensive in a way. Schlumberger invests a lot of money for the development of these technologies. But yeah, we do be provided for the students, because let's say when you are doing your projects, it's good to learn different technologies, because when you are going to get into industries, it's always good to have first hand, before going into industry. Maybe you can talk to your professors if you have a tie-up with Schlumberger, or maybe you can initiate, a tie-up program with Schlumberger in your country. That might help you to get, let's say, an actual version of the license. All right. So there are other software that I was talking about is Techlog. So Techlog, as the name says, Techlog Wellbore software program. Here the main focus is the wellbore. We will be doing multi-well work, but here the main focus will be on wellbore. So you can maybe, again, do a simple Google search. You will get to know what these softwares are. They are excellent softwares, quite handy to use, quite easy to use. We will see in the upcoming, time. There are certain training courses also. I mean, not sure if your college has some tie-up, but these training courses are organized by, again, Schlumberger. Next, there a dedicated software is also provided to you during the course of the training. That also you can opt if you want to, let's say, further get into the details. Well, you can find technical papers on the portal, as well as case studies. You can see different applications. Let's say we'll talk about Techlog Geomechanics. Let me play this video. I mean, if it is, let me see if you are able to hear the voice. Please tell me if you are able to hear the voice. Are you able to hear voice? Are you able to hear the voice, guys? Okay. Let me see if I can share.
No, we can't hear, sir.
Okay. See if I can share sound. Just see now.
Is fundamental to the performance of your asset.
Is it visible?
There are
Is
some
it audible
big
now?
questions you need to
Yes,
answer.
it's audible. Thank you.
Okay, I'll play again. Please hear it out. It's a nice video.
We understand that predicting changes in stress in the subsurface throughout the E&P lifecycle is fundamental to the performance of your asset. There are some big questions you need to answer. How can I understand the risks associated with drilling my first well? What type of well should I drill? What is the best completion? Will my casing withstand changes in pressure? What is the highest injection pressure? Knowing how stress is distributed in your reservoir enables you to answer these questions. Schlumberger software solves today's complex subsurface challenges by providing critical insights into the mechanical behavior of your asset and the surrounding rock. So you know where to place your wells and how to design the best field development plan. See how the health of your reservoir is changing over time. Determine the optimal depletion and injection pressures that will keep the reservoir seal intact. Understand if your faults will withstand the changes in pressure you are planning. And anticipate compaction issues before they happen. Schlumberger Geomechanic software puts all these capabilities at your fingertips. Designed to integrate seamlessly into the E&P workflow of asset teams, our industry-leading software gives you the knowledge, right answers to the big questions, so you can proactively control risk in the most effective way. and optimize the value of your asset throughout the life of your field.
So hope the video was good for you all. So you have these three technology tools. We talked about Petrel, which is a Wellbore related tool where we do the 1D modeling, one-dimensional model. We have Petrel where we do a 3D geomechanics model. There are other domains, there are other sciences also, like geology, petrophysics, reservoir, drilling. They are also present on these technologies, right? It's not only geomechanics, but through the different geomechanic applications that we have on Techlog and Petrel. So you can refer to this page. I will drop the link of this page on the chat box. Maybe you can just save it with you. Go through it in your free time. It will give you a some perspective on what these solutions are. And nowadays, Schlumberger, I mean, even many companies, but Schlumberger specifically is doing a lot of efforts in providing cloud services. All these softwares that you see, you might not require to install in your own machines. In the upcoming time, even in the current time, now what you can do is maybe get an access of these applications on cloud. Schlumberger, we have this environment called Delphi. It's a cognitive ENP environment where different softwares you can get it pre-installed. You can get access to whatever you want. It's something that everyone is adopting in the coming time. Again, it's good to learn about cloud-based applications and cloud platforms. Just go through it. Again, I'm sure in the coming time, by the time you join the industry, Delphi and other cloud applications will be heavily used. Now, the good part of Delphi and Delphi environment is, nowadays we talk about data science, we talk about analytical solutions, we talk about artificial intelligence, and these are the things which are integrated onto the Delphi platform. So that's the way to future, if I summarize it this way. You can go through it. I mean, there are a lot of videos. I will not play those videos for you. I will recommend you to go through it. It will give you a good understanding of what these tools and environments are. They are quite attractive. All right, so we talked about different applications. Coming back to my slide, as I said, 3D mechanical modeling, we'll be doing 1D modeling in Techlog. We'll be doing 3D modeling in Petrel. Please post those videos in Classroom. Where do I find this Classroom thing? Saad, can you please tell me where do I find this Classroom thing? Because I only see chat section with me.
Sorry, sir. I didn't understand. So
someone commented that I can post the videos in Classroom. Okay, later on. Cool. I will share the links again with Abel. All right.
The links with them later.
Okay. All right. So moving ahead. Model is nothing but you're trying to simulate your rock on your machine, right? On your computer, you're trying to represent the subsurface. That's the model all about. And model also always carries some uncertainties because model is as good as the modeler, right? The amount of data you have taken into account, the the uncertainties that you are taken into account. The quality of a model depends on many things, right? How well it is being QC'd, how well it has been calibrated. There are various things that that model has to be considered, you know. But as you acquire more data, let's say in exploration stage, you have a limited amount of data. You don't have much information. So the uncertainties with the model might be high, and which is what I'm showing in this red color. Red means high uncertainty and blue means low uncertainty. So as you acquire data at different stages of the development of the field, you will, let's say, keep on updating your models, both 1D as well as 3D, and keep reducing your uncertainties. Now, hereby I'm listing different applications. Let's say I will talk about these applications as we move ahead, but you know, pore pressure protection, wellbore stability, casing point, bit selection. There are so many applications of geomechanics that you can think of. There are a number of applications. I mean, almost all the operations you require some insights about geomechanics, like how the rock is going to behave when you are doing such operation, what value addition in geomechanics can provide. So it's a very versatile domain, you know, where it has the applications in all the operations that you do in the subsurface at all the stages of the life. I've tried to cover them, you know, on this slide. All right. So maybe, yeah, I will move to Techlog now. I will not invest my time maybe on showing you multiple slide sets and you will get bored. So let's look at it. Let's look at Techlog, how the Techlog looks like. So I'm not sure if you have seen Techlog before, but the icon of the Techlog is just like any other software, you know, Excel sheet or a PowerPoint. It's quite similar. So if you want to start any software, just double click, it will start. But these softwares, they require a license. You will be able to, let's say, maybe get a version from here and there, but you need to have a license, proper license to, let's say, be able to, you know, do different interpretation. Else it will be grayed out. Okay. So you see, it opened in my new different screen. So you see, my Techlog is open now. Now, just like any software, you know, even if you, let's say, create an empty document, Word file, you need to create a project, right, before starting doing any modeling. So that's what the software also requires. You need to create a new project. So what I did is I went here. You see, I went to new project. I will just create a project. Let's say maybe I'll just give it a name of SPE demo 1D. I'm giving a random name to it. Now, the next thing that probably you want to decide, so is the unit system. Most of the countries, they deal with field unit system. Many countries, they deal with metric unit system, and many countries, they deal with a customized unit system. That is that you will talk about depth in meter, but you will talk about the pressures in PSI, pounds per square inch, right? So most of the times in oil and gas sector, we deal with the hybrid unit system. That's why I have created my own unit systems. Maybe I'll show you how do you create your own unit system. But let's say for simplicity, let's take metric unit system. Then the other thing over here is the location you want to save your project. Currently, it is saving the project in my C drive. You can change it as per your need. You can also put the country. Let's say I'm assigning India over here. Project template, I don't have any as such, but if you have a template, I'll talk about templates. Don't worry, just forget what template means. You can add a description, you know, if you want. So here I just gave a name to the file, selected a unit system, and I'm going to go click on create. So you will see it created a, you know, it opened this software to me, and this is how the Techlog looks like. I'm sure most of you might be seeing for the very first time. if I may ask, have you guys completed the fundamentals of Techlog? Was there any session, or this is the first session that you are attending?
Actually, yesterday we saw just an overview of the reservoir characterization, and we'll do Techlog the next week. So you can say that it's the first session of Techlog.
Okay, great. So maybe I'll just give you a brief intro on the interface of Techlog, because like whenever you open a new software, there will be a lot of questions. You will have a lot of doubts: where to do what, where do I load the data, what option is used for what purpose. So Techlog is quite handy. I mean, first thing you have to understand, Techlog is quite easy. It's just like any other Microsoft applications. So let's say if I press Alt from my keyboard, you can see just like any Microsoft applications these days, you will have acronyms corresponding to different menu items. First of all, let's look at the different menu items. You have home, right, where different options are there. You have plot. The name is intuitive enough. Plot means you want to visualize your data. You have different visualization options. Home is for default settings, different windows. Plot is for visualization options. We'll talk about them. Don't worry. Just have a broad understanding of what options, what menu items Techlog has. Then you have a tab called data. So these are different tabs. You have data tab. We'll go through it. Then you have utility, studio. So see, since I am a Schlumberger employee, I have access to most of the applications. Whenever you operate a Techlog software, you might not see all the applications. You might not see petrophysics being active. But for me, everything is active. As I said, Techlog is a place where we do interpretation of various domains. It's not geomechanics. It's not just geomechanics. We do many experts. They use Techlog for different purposes. Even geologists, petrophysicists, they also use it. Even reservoir engineers, a lot of engineers, they use it for their own purpose. But the most common part would be, we'll always go to home tab for some of the features. We'll go to plot tab, to visualize the data that we are generating. We'll go to the data editor part, or data options. We have certain utilities. Nowadays, most of you might be learning Python coding. So Techlog has integrated Python environment where you can write your own scripts. You can write your own workflows and do the modeling. That is also very much feasible. Studio, maybe I'll cover it later, forget about it. Then you have petrophysics. We'll not be covering, let's say, many applications here. I'll see what I can cover here, but our main focus will be on geomechanics. So this is the tab which we intend to cover in the 2 sessions which we are going to have on Techlog. There are various things. There are various models that we'll cover. There are various concepts that we are going to cover. Don't worry. We'll cover in good detail. Very similar to it, you can see there are different tabs. The names are intuitive enough, and they will tell you what these applications are. These are different applications. There are different domains in oil and gas sector. Depending on your interest, you can start working on either of the available options. But being a geomechanics engineer, these are all the options that I have to deal with. Very basic operations that I need to deal with. All right, so as of now, we have just created a as of now, we have just created a project. We have given the name as SP Demo 1D. On the top, you can see. On the next, also, you can see the version of the Techlog I'm using. Current version that I'm using is 2020.1.3. This is the year, this is the, subversions. All right. Apart from that, let's get bit used to the different windows. So you can see something called project browser. You can see I'm just dismantling my Techlog. Maybe first time you will open, you will not have Techlog the way I am having. Maybe I'll just shut down everything. I'm closing every window that was visible to me. So maybe first time that you open your Techlog, you will have something like this. You will have menu options. Under these individual tabs, you have different items beneath them, and you might not have any window, right? So you might be clueless where to do what. The Python class is at 2:30 p.m. GMT. Okay. All right. So let's go to let's understand how do you organize your Techlog. Which windows are essential, because you want to load the data that you acquire in a field, right? So you want to visualize the data. What are the windows which are very much essential? Let's look at those windows. So under home, you see there is something called view option, and under view you have different options, and one option is dock windows, right? So under dock windows, the most important window for Techlog is the project browser, right? This is the most important window that you will require whenever you practice on, let's say, any modeling in Techlog, be it geology, geophysics, anything. This window is quite useful. Now, as soon as I toggle on project browser, you saw that, this window pop up. Now, what I can do is I can maybe put it, I can put this window on the left side of my screen. You can see using this option, I can choose where I want to place this particular window. So, okay, so I have docked this window on the left side of the screen now. You can also dock it, let's say maybe, on the right side. You can also dock it on the bottom side. Again, it's your priority. As a modeler, I always prefer to keep it on the left side of my screen. I have a multiple screen, that's why it is giving me option in my other screen. But yeah, you can also always choose a suitable location for the project browser. Now, what project browser includes? In project browser, you have this symbol, symbol of a rig. You see, it is the place where you will see all the wells, the data set of the wells that you are going to load. You can see another option, the square box. It's the displays that you create. These are different visualizations, log view plots, like a cross plot, a bar chart, any plot that you are going to create, you will observe under this particular display option. Then you have Python scripts. If you are good with Python, you can create your own Python scripts and develop new workflows. You will be able to see it over here. Then you have cross plots. Cross plots are nothing but two variables, one on X, one on Y. You can create different cross plots and it will be saved here. We'll talk about what this option means. This is sort of a neural network workflow. If you are working on a neural network based workflow, it will be saved over here. All right, there is something called recycle bin. At the end, you can see this box, just like a Windows option. Yeah, this is a recycle bin. If you delete anything from your project browser, from your project, it will first go to recycle bin. And if it has happened, let's say by mistake, you can restore it. So it's quite handy. Understood everyone? You all understood what does the project browser do? How do you dock project browsers? This is the first window that I have talked about. I haven't loaded any data. I haven't done anything. I'm just telling you, what is the use of this window. This will be covered, I guess, in the Techlog fundamentals. But yeah, this is a very handy window that we'll be using, throughout the class. So I want you at least to get used to the names, because I'm not sure if the words are very much clear to you. Okay, the next thing that you want is the properties. The next thing that you want is properties. Now, why I need properties? Because you want to change the scale of the logs. Let's say a density log. Are you guys clear with the log data? What does a log data mean? You all clear, right? Okay, great. Yes. So in a log data, now you might require to change the color of the log. You might want to display density in red, with a scale of 1.8 to 2.8 gram per cc. You might want to change thickness. You want to do a lot of changes. You want to maybe do a lot of changes with respect to visualization. So every change that you want to do, you will be using properties tab. Properties tab is the properties window is the area where you will always go to do any modifications with respect to visualization or changes. All right, so you can see it is empty because we don't have any data loaded in our Techlog. That's why it is empty. But this is again the second most important window that we are going to use. Apart from that, we will be using something called zonation. So in oil and gas sector, as we are very well aware that subsurface is divided into different geological sequences. Different formations are deposited in different time zones, and these formations are given different names, which we call at formation tops, right? These formation tops carry their own significance in the area. It varies from client to client, area to area, country to country. But in general, we call them as zonations, zones. These can be, simple geological ages like Miocene, Eocene, Paleocene, Cretaceous, Jurassic, etc., Permian, or it may be just the names that are locally assigned. So that depends again, but this is again quite important. You want to see what formations you are going to deal with. As a modeler, you have to be very well aware that if you are doing a modeling for Jurassic age rock, or if you are modeling a Miocene, very, very young recent formation, because you understand the older the rock gets, it will have very different properties. That's a very understood phenomena, right? If you are talking about very, very old rocks, Cretaceous, Jurassic, or even maybe Cambrian, it will have a very different behavior and a property as compared to a very recent shallow, let's say Miocene sort of formation, which is very recent. Maybe you can go to a beach, you will see a clay on the near the beach, and it will have a very different behavior in comparison with a rock piece that's a boulder kept near the beach, right? It will have a very different behavior, and the behavior you can understand is maybe you can try a sit on it. If you sit on a clay mountain, you will see that it gets compressed, right? If you sit on an igneous rock, which you would always prefer to do that, if you sit on an igneous rock, it will not get compressed, right? So right, so zonation is quite important. I prefer to keep my zonation tab just beneath my project browser. Again, see, these priorities, they vary. It's not a fixed pattern. I can keep it anywhere I want, but as personally, I prefer to keep it beneath my project browser. But the idea over here is you can keep your zonation tab anywhere you want. All right. Apart from that, as a beginner, since you are starting Techlog, you'll be working on Techlog for the very first time, you need something called output. Let's say most of the times when we do mistakes, now software ultimately you have installed on a machine, right? It's a machine. Now, if there is an error or a warning that software is trying to communicate, it will communicate via output pane. If there is an error, it will it will show you a message in output pane. What is the error? What outputs are computed, etc. Right? It's a medium to communicate with the workflows. So I will also try to keep output at the bottom of my interface, so that you are aware that what is its use. Apart from that, I will not toggle on other windows. See, there are a lot of windows. Don't worry about them. We'll see how much we can cover. But these are the three, four basic windows which are very much essential. The other things that you have to be comfortable with is a tab. So this is the empty space where different displays will be there. And you can divide these displays in tabs, just like a Google Chrome, any browser. You can open different tabs, right? You can see at the top, I can click on this plus sign and I can create multiple tabs. Now, in different tabs, I can do different works. Maybe one tab is for one well. You can divide, right? This option is also very handy. Let's say if you are working on multiple wells, you can create different tabs for different wells. There are different purposes for which you will create different tabs. So I'm keeping only one tab open now. I will, whatever I'm going to do, I'll do it over here. All right. Apart from that, there are some other features also. So what I did is, you see just this option, 3 lines. These are some of the options which are quite handy. So I'm going to options. So you see, whenever you start Techlog, by default, it will restore the latest session, the last session that you are working on. By default, it will choose that. There are some other by default rules, like Techlog has the default rule of saving the project after 30 minutes. After every 30 minutes, it will save the project. right? You can change this to maybe 10 minutes or 90 minutes, depending upon like how much. I see that these marks are created by some students. I don't know how, why it is being done. I'm not sure who is doing it. Okay, let me remove them first. All right. So you can change the default settings of the Techlog, right? Workspace preview, you can choose if you want to have large, normal or a small preview. You can change the fonts. There are all default options that you want to choose. I have created, let's say I have kept a dark gray background. You can choose a different background. You can organize your different log views in this different formats by default. So I have some customized settings for myself because we work on different projects on day-to-day basis. And this is something that, user has to define on their own. But the important thing here to tell you is you can customize your settings. You can customize your own Techlog for yourself as per your own requirement. You can define what the null value means. You can define how you want to visualize your data, things like that. All right. So maybe now let's start loading the data. Is this clear, guys? I have just covered how the Techlog looks like, what are its different windows, what are its different menu items. I haven't touched any part of it. I haven't done anything as of now. I've just covered what does the Techlog look like and what are its interface and different menus. Okay, great. All right, so let me tell you a few tricks. As I said, if you press Alt from your keyboard, you will see, just like in any Windows application, you will have different shortcuts assigned to different menu items. Let's say Geomechanics assigned C. When I press C, the shortcuts will now assign to different tools under Geomechanics, different workflows. And if you want to open, let's say, overburden stress, you can press S, right? So you can operate Techlog with the help of let's say, mouse, or you can also operate Techlog using a keyboard. But I would always recommend to keep a proper mouse for operating Techlog, because visualization and handling multiple things in Techlog, it's quite easy on a mouse, separate mouse. You will be having some trouble if you, let's say, operate on your notepad, your mouse pad of your laptop. You might face some problems. All right, so let's load some data now, guys. Let's load some data. So you see, I have some data with me. I've kept it ready for you all. So you might be aware of different data types. You might be aware of LAS format. You might be aware of ASCII format, right? There are different formats in which a data is saved, right? There is a DLIS format. You might have a data in Excel sheets. So there are different formats of the data, right? There is something in XML format. So you have to first understand what type of data you have, right? The log data, you might have it in different formats. So here I have data in XML format. Doesn't matter which format you have actually. For Techlog, it doesn't really matter. It's quite, it understands the type of data on its own. So what I'm going to do is I'll select all the data with me. You can see I just press Control A. I selected all the data with me, right? I selected all the data with me. What I'm going to do is I will just drag and drop my data into the Techlog. You can see it is loading. I had nearly, let me show you, I had nearly 2.4 gigabytes of data, and you see Techlog has loaded in 30 seconds, right? So is it fast, right? Techlog is quite fast in loading the data. So I had nearly, so many files. Well, see, there are now, the data is released by many companies on different portals. Europe has some public data set. I would recommend you to go through those portals, because, I'm not authorized to share data directly with you, because we do have some MOUs, with clients who have shared the data with us. But nowadays, see, there are a lot of data sources available online. You can just grab some data there. Doesn't matter which well, which field you are working on. You need to practice, right? You will have a lot of data. Maybe I will try and share those links with you where you can find data. But there are various online repositories there where they are where they have shared, bulk amount of data. Good amount of data has been shared. I will keep a note of it, guys, and we'll share the data set, or link of the, let's say, portal where you can download the data. All right. So this data is no unique. It's a very random data that I'm taking. Doesn't matter which data set you are working in. You just need to get used to the interface, right? That's the objective. So you see, I have what I did again. I'm repeating my steps. So you see, I had these. I have so many files with me, right? I had so line items. I selected all the line items. What I did is I just drag and drop all the line items into Techlog. I didn't do anything, right? Once I drag and drop, like any other software, it will try to understand what does that data means, right? Now, if you look at the format of the last file, I'm not sure if you are aware of the format of a last file or ASCII or a DLS, but the formats of the data, the format of the file that we use in oil and gas sector, they have a certain, structure. These are the structured database, structured data types in oil and gas sector. They do carry some information about the well the data belongs to. Give me a minute, guys. So give me a minute. All right. So I was saying that you might have data in different formats, right? As soon as you drag and drop a data set into Techlog, it will try to understand which well it is and what is all the information it this particular file has. So you see, first thing that you have to understand is, you see I have loaded all the data files. Now Techlog by himself, it has now identified this symbol is for the well. So there are, how many wells? You can count 4, 6, 7. There are total 11 wells, 11 wells data set that I loaded in just fraction of seconds, right? So once you do this, what you need to do is you need to take all the data into your project. So as of now, what I did is I just drag and drop my data set. Techlog understood what are the wells this data contains. I need to decide which well I need and which well I don't. At times you just want to load the well which you want to model, right? You don't want to load the entire fields data set in one go. You want to probably limit yourself to one of the wells you want to model. So, but here I'm loading all the data. So loading is also very easy. You see this import option. So as soon as I drag and drop this data set, this import window came up where I'm able to see different wells, and I selected all the wells and I chose this import option which is helping me to load the data into my project. Now, as soon as I'm done, I'm deleting these intermediate files and switching off this import wizard, right? So you see what I did very simple steps. I had this import wizard. So under home, you see there are multiple ways of loading data set. I just told you one way. So under home you can see this import wizard, right? If you click on import, you can manually go down here and choose the data that you want to load, just like any software. But Techlog, I guess the best part would be to just drag and drop and load the data set, because it's quite handy that way, right? But you can also click on import, choose the type of file you have. Guys, give me a minute.
Sir, can you hear me?
I can hear you. Give me 2 minutes, Chief. I'm coming back.
Okay, thank you.
Okay. Sorry for the break. All right. So hope you understood, like, how do you load the data? There are two ways mainly. Once, if you want to do it, let's say conventionally, you can go to home and click on import. This section will open up. You need to choose the type of file you want to load. If you want to load an ASCII file, an XML file, and then choose the location using this particular folder. Choose the location where the file exists. This file will open up over here, and then you can import. But I guess, see, everybody wants to do it quickly, and the quickest way of loading the data is to select the well, select all the data set, just drag and drop like I did again, right? It will identify itself. It will identify itself, like what wells it has, what data set it has, if it's the image data, it's a log data, it will identify himself, and it will show you. You load the required data set into your project, right? And we are done. We are done with the data loading part. Cool. Is it clear? Is it clear, guys? Are you able to understand the data loading part? Is it clear? I know you are not doing hands-on with me, but at least understand like what I'm trying to convey, and you can send yes or no in the chat box so that I can understand. Shall I? Okay. Okay. Great. Okay, great. So data loading is very easy, right? Data loading is very easy. And you understand different type of data sets that you might have in oil and gas sector, right? We have DILIS, LAS, ASCII, you have different type of data sets. Now let's say if you have a data set in an Excel sheet, let's say if you have some data set in an Excel sheet, maybe let's create some data set. So I just open an Excel sheet, right? So let's create some data, and let's say I have MDs for measure depth. Let's say I have something called, are you guys aware what is MDT? MDT is recorded pressures. Let's say you have MDT, measure depth of the MDT. Maybe, let's take 1500, some 2500 PSI. Are you guys aware what does MDT mean? Or let's take it as formation pressure. So see, geomechanics is an application domain. There will be a lot of words that I'll be using. If you don't know any words, please do let me know. Or maybe I'll just try to introduce those words with you. All right, just let me know when you have some doubt. Yes, MDT means modular dynamic tester. MDT is a tool which is used to measure the formation pressure downward. It's just like a logging tool which is used to measure the formation pressures, right? So let's say at a depth of 1500 meters, let's say this depth is in meters, formation pressure is in PSI. It's the unit of the, maybe you have, I'm just creating a random data set. I'm assuming that, let's say you get this data set from somewhere. At a depth of 2000, I have a pressure of maybe, let's say 3500. This is a random data set I'm having in an Excel sheet. Now, if you want to load this data set in Techlog, how you are going to do it? There are multiple ways again. I'm telling you one of the quickest way. What you can do is just copy paste. So you just have to do a control C, that is copy, right? I just copied the data set, and you can see over here, import from clipboard. So as you are aware that when you copy anything on your system, it goes to a clipboard in the system on your machine. And from that particular clipboard, you can just directly import it into Techlog. You can see as soon as I did that, it took the data in Techlog. Now it is asking me, it has opened up this window, data import wizard window. Why it is doing that? Because you see Excel sheet, I mean, it's not a LAS or a DILIS or a ASCII format. It doesn't have a well name. It doesn't have a reference defined. So it is asking me, how do you want to load this data set? It's a data import wizard that pops up. So just like an Excel sheet, you need to decide, right, which line, from which line you will have your units, from which line you will. So you see over here, line 1 has the name of the variables, line 2 has the units of the variables, from line 3 I have the values, right? So I need to define that, right? Software might not understand on its own. So I need to define that the variables are in line 1, the units are in line 2, and I need to import from line 3, right? I need to import from line 3. You see, as soon as I did that, this got updated now. My variable name is measure tab. My second variable name is formation pressure, which I had in an Excel sheet. Its unit is in meter and its unit is in PSI. And these are the values that I had in my Excel sheet, right? Now on the top right, you need to select which well it belongs, right? You need to load a well data into a particular well. This MDT might have been recorded in a particular well. So you need to select which well it belongs. You need to select the well it belongs. You can give a name to the data set, name of the file, like, this is an MDT data set. I gave MDT data set. You can define its type. There are a lot of other things that you can do. All right. So once you do that, you can see I can load this into Techlog. I had chosen W4. You see, it has loaded the data set into W4. All right. And the name of that particular file is MDT. I can again select this and load this back to my well. You can see under W4 well, I have loaded the MDT data set. Correct. So no matter what type of data set you have, you can load most of the type of data sets with respect, which is recorded in a particular well. It could be temperature readings, it could be pressure measurements, it could be anything. It can be core data. All right, so I'm deleting this file, and let's say if you want to delete any file, you just need to press delete from the keyboard. So you see, I chose MDT, press delete, and I am able to delete this particular file. As I told you, as soon as you delete, it will not go, it will not vanish from the project as it is. It will go to the recycle bin. If you want to restore, you can restore. If you want to permanently delete, you have to press shift delete, just like Windows, right? Understood, guys? How do we load data set from, let's say, an Excel sheet, raw data set, which is not structured? It's easy, right? It's easy. All right. As of now, we haven't I haven't started, even with the first step of geomechanics. I'm just telling you some basics that probably we will be using when we do our model. Now, let me tell you about the few more things about the structure of data in Techlog. How does it look like? Okay, let's say now here you are seeing different wells, right? You are seeing a lot of wells. It might be confusing. Let's say the name here, training well underscore well. The name itself is not good. You might want to change the name of the file. So how do you change the name of a file in Techlog? So the first thing that if you don't know anything, just right click. You will always find some options. Then you can read through these options. What options do you have? Do you have rename option? Yes, you have. What is the shortcut? F2. Now in Windows also, if you want to rename any file, you need to press F2, right? The same goes for Techlog, as I said. The shortcuts are kept very similar as Windows. So I will name this particular well as, let's say, well A, right? Well A. Training well underscore well was a little confusing. And I don't want to see all the other things. I want to filter it out. What you can do is, again, right click. You can see there is an option of create a filter. The shortcut is Control J. So I will press Control J from my system. You can see other wells are gone. They are there in the project, but not visible. And I don't want to see them because it might be an extra confusing. And again, depends, right? I don't want to see them as of now. I don't want you to get confused with so many data sets. All right. Okay, so let me introduce you the different type of data types we have, different type of data sets that we require in Geomechanics, and how do they look like in Techlog. So So this symbol is clear, right? This symbol is a symbol for well. I'm not sure why students are able to, you know, do annotation on my screen. Can we stop doing it, guys? I'm not sure why we are doing it. Do the students have access, Nabil? Can they do annotation on my screen? I don't know why they're doing it. Who is doing it? Anyways, okay.
Yes, sir.
I see that students are able to, you know, do annotation on my screen. I don't know why and how. Okay, just let it be. No worries. Just be a bit careful, guys. All right. So moving ahead, you can see. Let me introduce you to different type of data sets we have. So you are clear with this rig symbol, right? Which is a symbol of a well. Now under this particular well, you have different data types. You are able to see different symbols. Again, this circular symbol is a symbol of a group. So these 4 line items have been grouped under calibration. Calibration data is something which is very useful. That's why I have categorized as a calibration. You can name it something else, right? Then you have a name FMI. FMI is a resistivity image. It's a type of resistivity image. So that's why it is grouped under FMI data. Then you have formation tops. You have something called LQC, logs which are QC'd. You have something called survey, and you have something called zonation all, right? So first understand the type of data sets. Let's see how does the core data looks like. Or so for that, what I'll do, I'll go to data editor. Now data editor is a place. It's just a very similar to Excel sheet. So on Excel sheet, what you do is just display the values, right? So if I want to display, let's say what is there in the core data, I will just drag and drop my core data in this data editor. Data editor is a window, just like an Excel sheet. I'm trying to visualize what data I have under core. So you can see this core, first understand this is a point data set. How do I know it's a point data set? You see these three symbols. So this is an indicator that this is a point data set. That is, the readings are available at a particular point. All right, you see at these 2 depths, you have readings of friction angle and something called UCS. Right, this is a point data set available only 2 depths. Let's check out the data set named F pressure. If I do this, it will ask me if I want to resample there or not. I created another tab. You can see this was the core data. I will close it. Now this is the pressure point data set. I drag and drop pressure data set into data editor. I am able to see different data points. You can see, right? Don't worry, I'll maybe cover those in detail. Here we are just trying to visualize what data we have and how does it look like. So this is a point data set. Same goes for LOT. You have point data sets, you know, different depths and different values or different curves. You have mud weight, right? MD, ECD, mud weight, mud pressure. So if you are not clear with any of the term, please do let me know, because again, it's a vast topic. I might not be aware what is this. I mean, I'm not sure if you are aware of the term ECD, mud weight pressure. You know, what does those terms mean? Maybe I'll try to cover them briefly. All right. So unless you tell me, I will swiftly go through them. All right. So these are all the point data sets. You see, these are all point data sets. This you can recognize by their symbol. 3 dots means point data set. This is a point data set. Now then comes a continuous data set. Continuous data set, because we know in oil and gas sector, let me open a whiteboard. Maybe I'll try to briefly. What does a circle represent? Circle represents that it's a point data set. These 3 dots that you see on the this particular folder core, it means that it's a point data set. Point data set. right? In oil and gas, so you have your rig, right? This is your ground level, let's say, and you are going to drill a well, right? This well might go down 3 kilometers down the subsurface, right? 4 kilometers subsurface. It can go as deep as we want or as it is being planned. Now you do some measurements, you do acquire some measurements, right? You acquire some log data. Now this log data can be of continuous type, can be a point data, right? Now let's say if I talk about MDTs or formation pressures. Now MDT is a name given by Schlumberger. Other vendors will have a different name, RCI, or XPT or something like that. But this is again tool. This is a tool or technology which is used to measure the formation pressure, right? And it was acquired at a particular depth. Let's say you go down, you put the tool into the hole and you acquire pressure measurements at these 3 individual depths. So that's why the MDT data type is point data, because it is only available at 3 depths. But if I talk about continuous data type, it will be available. So the continuous data type, it will be available from one depth to other, and it will have some sampling rate. Let's say after every 0.5 feet, there will be a reading with you. You will have density measurements at every 0.5 feet. It's a point data, but it's a continuous type of point data. And every point has, every point is at a distance of 0.5 feet from its nearby point. Okay. So when you plot this data in an Excel sheet, it will look like a continuous data. That's why we always call it a continuous data. But we always know that even line is just accumulation of different points. Clear? So you have continuous data, you have point data. Continuous data will be continuous in nature, right? It will start from some point and it will go to a certain point. Continuous log like data provides from DST operations. Well, yes, DST operations, they have data types in time format. You have one as one axis as time and the other axis as pressure. It will act as a continuous data type. You have other data types like density. You have data type like gamma ray. Are you guys aware of the wireline measurements, DNM measurements? These are different segments which acquire data. Are you guys aware of wireline operations? Have you heard of the name wireline, DNM, wireline tools? Guys aware of it, right? So see, you have to do some homework there. There are a lot of terms I'm continuously taking. I'm not sure if they are very well understood to you all. You have to be very well versed with different technologies in oil and gas sector before doing any modeling. See, if I don't know what does the term gamma ray means, what is a gamma ray? If you don't know the gamma ray law, you will be in deep trouble. Because see, we are doing geomechanics, means we know at least we do have some basics. We do have some basic understanding of what does the different measurements means. Let's say if I talk about bulk density, right? Bulk density. So I have to be very well aware what does the bulk density means. If I am talking about gamma ray, I need to know what does the term gamma ray means. What does it indicates? Else I won't be able to do modeling. I won't be able to utilize it for interpretation, right? You need to have some understanding of the basic logs. So this will be an assignment maybe for you all to understand what does the basic logs are, what are the basic logs and what are its meaning, because throughout the sessions we will be using them directly. All right. Okay. So now let's say instead of looking the data in a data editor, which is just like an Excel sheet, we want to visualize them better. How do I visualize them? So I'll go to plot. The first option is log view. You see option of log view. Now in log view is a place, it will open a window like this, and log view is a place where you can visualize the data. You can see I opened my LQC. I am just expanded in. I just expanded the this LQC container, and you can see different acronyms. So BS is for bit size, C1 is for caliper, DTCO is for compressional slowness. It's a sonic measurement, just like it's the is equivalent to the velocity of the wave. It's inversely related with the velocity of the wave. Okay. Then you have shear velocity, you have P velocity, you have shear velocity, you have gamma ray, you have caliper, resistivity, part one orientation from, you have PEF, total porosity, bulk density, neutron porosity. These are all different log measurements. Now these are all continuous data sets. How do I identify if it's a continuous or not? You see, these are three different dots. So these are different identifiers which we use to understand if it's a continuous or a point data set. So now you see this LQC data set, there are different straight lines. These are different lines, right? It tells you that it's a continuous type data set. In addition to that, if you look at the point data set, let's say over here, you see these are different points corresponding to LOT MW. You have different points. Sure, I can send you some link to Geomechanics. So do you guys study any relation? Do you guys study rock mechanics in your subjects? If I may ask, do you guys study rock mechanics? Do you guys understand the terms like stresses, strains? Do you guys understand? You guys understood? Do you have any session on it in your curriculum? Okay, nice. Soil mechanics is very much relatable. So at the end of the day, we will talk about stress strains in geomechanics. Most of the times we'll talk about stress strain, Young's modulus, Poisson's ratio. We will talk about all these terms. But in order to talk about all these terms, we need to know what are the different logs that we have. In oil and gas sector, we acquire some data, right, by different means, and they have different acronyms as you have it over here. So let me show them how do they look like. Let's look at the gamma ray curve. Gamma ray measures the radioactivity. See, give you a brief idea. So you can see what I did in order to plot gamma ray in Techlog. It's quite simple. What I did is I just drag and drop my gamma ray into the log view. Remember, I opened the log view. I'll do it again for you. I've opened the log view. I just drag and drop the gamma ray. You can see I am gamma ray, this particular curve GR is plotted now, right? On this axis is the depth axis. This is depth, which is called here as reference. And this is gamma ray. It starts from 0 and goes as high as 150. This is the default units that my gamma ray has. Let's say if I want to see, if I want to zoom in or zoom out or maybe change the scale, the way you can do it is press Control from your keyboard. Okay, I'm repeating, you can keep a note of it. I'm pressing Control from the keyboard and rotating my roller of the mouse. You can see I'm able to change the reference scale. I'm able to see the whole of the data. I'm able to see the start and the end point of my data set. So these two tools you can use it to read of the values. So data starts from 528 meters and it goes as high as 20 to 11 meters, right, from top to bottom. And you can see gamma ray is reading different values at different depths, right? Somewhere it is low, somewhere it is high. Okay. So you haven't done any interpretation as of now. I am just telling you how do you plot the data? How do you visualize the data? Let's say if I want to see the scale on reference, I selected my reference. Remember properties tab, anything related to visualization, you will go to properties tab. I selected my reference track. You see this option, use the reference of the layout. Instead of that, I will choose, let's say, interval of 200 meters. So I can see interval of 200 meters. So visually it is appealing, right? I'm able to see how the data look like at every 200 meters and what are the depths. Similarly, you can plot the resistivity. right? Now, in order to plot resistivity, again, you just select the log. See, I know by myself that HLLD means resistivity, but you have to, probably clear out some basics. Acronyms might not be very handy to understand, but you can see in Techlog, in addition to the acronym, that is HLD, you have something gamma ray. You see, I was talking about the family named gamma ray. Yes. Now, family is very important. So, resistivity can be measured by various tools. Now, resistivity can be measured by various tools, right? There are lateral log tools. There are other tools which you can use in oil and gas sector. And we need to assign a proper family to them. What does the term family means? So you can understand, let's say, now in a family, there will be different child, right? Just like a family, you have different kids, you have 2-3 kids, right? Very similar to that, that. Let's say you have a gamma ray family in Techlog. Very similar to that, we have gamma ray family in Techlog. Now, there are different tools for gamma ray. There are different type of gamma rays. So all these gamma rays will fall into gamma ray family. Okay. It has its own usage. I will tell you its practical applications and implications when we do start modeling. But gamma ray family will have different gamma ray logs, gamma ray measurements. Just like resistivity family, it will have different curves, different logs under that particular family. And depending upon its application, we can choose the best one for our own purpose. Yes, we can put the logs into the same track. So there are, again, let's say, so you see when I choose, let's say, compressional, when I'm dropping, you see, when I'm dropping the particular curve, there are two blue tracks, one over here and one over here and one over here, right? So this is telling you where you want to drop. If you drop on the left side of the reference track, it will get created on the right side. But let's say if you want this curve to be created prior to gamma ray, you can drop in this blue track. You see, now it is created over here. If I want to, let's say, add gamma ray on gamma, if I want to add compressional DT-co on gamma ray, you could just drag and drop on the gamma ray. You see, both the curves are on that same track, right? Now, if you want to, let's say, move, if your mind changes somewhere in between, you want to change gamma, if you want to, let's say, move gamma ray to a different track, select gamma ray using mouse and press right from the, right key of your keyboard. Right, left, right, left, right. You can shift your log measurements onto different tracks. It's quite handy in Techlog. All right. You can also see that different logs have different scale, right? Compressional slowness is measured in microseconds per feet, μs /feet, and it is plotted from 40 to 240. Now, in an oil and gas sector, it's a standard way of plotting log, right? And how software is able to do it? Because of the family. As I said, family, defining the family of the logs is important in Techlog. It does it by default, but at times you need to define it on your own. Now, the benefit of defining a family or assigning a family to a particular log data is that it will assign automatic units. Let's say if you assign gamma ray its correct family, so whenever we are going to plot gamma ray, it will plot from 0 to 150. You can change these defaults, no issue at all. But if you don't assign a family, the software will not know what type of measurement it is. Right? It will understand the units of the density. You might have density in kg per meter cube, or you might have density in some other unit. But in order to make software understand, you need to define proper unit system as well as family. Understood? So likewise, you can plot, let's say, caliper log. Caliper measures the dimensions of the wellbore, right? So you have caliper is measured in inches. Similar way, you have neutron porosity, you have density log. You see, RHOZ means density. It is measured in 1.8. It is measured in gram per cc. You have neutron porosity. Usually in oil and gas sector, right, we plot neutron porosity, which is TNPH, on top of density, bulk density. That's why I have followed the same. Right. If I want to shift a track, let's say if I want to shift this track on second position, you can do it. Just select that track and maybe use your keys up, down, right, sorry, left and right keys to shift your tracks, right? You can see I'm able to shift my tracks, right? So moving tracks here and there, moving curves here and there is quite easy in Techlog. Let's say if you want to change the color of the log, if I want my resistivity, which is this HLLD curve, I will select this HLLD curve and go to properties tab. As I said, anything with regards to display, you will go to properties. I selected this curve, I go to display and I will change the color from red to, let's say, blue. I mean, depending on what you want and how do you want to display. If you want to change this particular curve from a solid line to dash type line, you can do that, right? You can change its thickness. So there are different tools. So Techlog is a great depth in visualization. So you can change, you can do a lot of modifications with respect to visualization. So as of now, you see I changed the color of the resistivity from red to blue, and I change its thickness from 1 point to 2. All right. Until this point, it is clear, guys. I'm not sure if I'm too fast, but I'm trying to be very slow. I'm trying to cover the basics as deep as I can. Great. Please feel free to stop me anywhere in between if you have any doubt. All right, so you clear. So this particular window is the log view plot. You see, this is a log view plot. Most of the time you will see that the petrophysics or geoscientists or geologists or operation geologists, they prepare a plot like this. They want to interpret different formations or they want to interpret reservoirs. They use a plot like this, right? So you can create a plot on your own and use it for different purposes. This is just a visualization track. This I can change the scale of this track as per my own will. Let's say if I want to zoom in. So you see there are multiple ways. Yes, you can do that. Let's say, let me show you how do you do that. So first, let's understand how do you zoom in and zoom out. At times you might want to zoom in into your plot, right? So if you want to zoom in to this plot, what you have to do is press the wheel of the mouse, and drag your mouse inside ahead. Like you see, I'm able to zoom in. And if you drag the mouse backwards, pressing the wheel of the mouse, it will zoom out. So you can zoom in and zoom out, right? You can see. If you want to change the scale of the plot, currently it is in 1:7,000. If I want to, let's say, reduce it and keep it around 1:500, what you need to do is press Control from the keyboard and just scroll the ruler. You see, I'm able to change the scale. You can try this out once you have access to Techlog, but yeah, you can squeeze your plot. You can extend your plot as per your own requirement. You can zoom in, zoom out. These features are quite handy. If you want to do it by default, if you want software to do it, these are some default options: horizontal adjustment, vertical adjustment. You see, as soon as I press these, it will get changed as per the option I choose. Now let's understand how to do shading and all. Let's say I have HCal. HCal is the caliper, and you have the bit size, right? Bit size. So this particular data is from a 6.75 inch wellbore. So the bit size is 6.75, and this is the actual caliper data. So many of the times interpreters want to shade the region between caliper and the bit size. So what you can do is select both the curves, pressing Control, just like any other Windows application. You select both the curves using Control, right click, and you see on the top, insert area, fill between the variables. As soon as I do it, you see it has shaded yellow between bit size and caliper, right? And brown between caliper and bit size. So there are two regions, right? The one above the bit size and one below the bit size. The one below the bit size is shaded in brown. The one above the bit size is shaded in yellow. If I want to change yellow to some other color, you select this particular shade. You again see the properties window. We will always use it, quite frequently. Change yellow to, let's say, this color over here. You see, I'm able to change the color. If I want to change the pattern in which caliper is displayed, I will again select the caliper, go to display. Instead of a dot, I will select solid line. Instead of red, maybe I'll select black, right? So you can do a lot of visual changes. I mean, anything you want to do, any plot, you can beautify your plot a lot in great detail. Let's say if you want to change the font, what you need to do is select all the curves. Now, let's say in Windows, if you want to select multiple files, what do you do it? Select first file, select and press Control or Shift. Select the last. You will be able to select all the logs in between, just like files, right? Or if you press Control A, it will be selecting everything. That is also possible. So I'm selecting all the curves in one go by pressing Shift. I will go to again my Properties tab at the right hand side. I will change the font. Maybe I will choose a Arial black font and a different size, right? You see, I'm able to change the font type also. So now Gamma Ray is Arial black. Increase its font size so that it is clearly visible to you all, right? If you want to delete anything, just select that particular thing and delete, right? Press delete from your keyboard. It will be deleting that. If you want to change the color of Gamma Ray, which is most of the times kept as green, you can go to properties and choose green color. All right. Is this clear, guys? So you see, we have created a very basic template, very basic log view where we are able to visualize the data that we have in well A, right? In well A, we have different log types. We had gamma ray, resistivity, neutron porosity, density, bit size, caliper. We are able to plot them. And we are able to understand one thing from this, that let's say in this particular area, your hole is bigger than the bit size, right? The hole is bigger than the bit size. That's why you see this cyan color, this light blue color shade, right? In some of the regions, like over here, you have the hole size lower than the bit size, right? It might indicate that presence of a mud cake, right? The hole is lower than the bit size. That might indicate that there is a presence of a mud cake. This is one of the many possibilities, right? You are also able to see the pattern, the variation of the gamma ray curve. You are also able to see the variation of the density, right? You are able to read off the values. You see, the Techlog is different tools. This tool over here, this tool will help you to read the values of different logs, because visually it will be very difficult. You will have to read, by looking at the different divisions. Let's say gamma ray starts from 0, goes to 150, and this particular track. So this is a track. This track is divided into 5 units. So each unit will be of 30 GAPI, right? So each unit is 30. So that way you might need to read off manually, but if you toggle on these tools over here, you can just interactively read off different values. You can see I'm able to read off gamma ray, depth, resistivity, density, porosity, caliper, bit size in one go, right? You have readers also, you have reading tools also. All right. So now what I'm going to do is I'm going to save this particular plot because let's say next day if you come to your machine, you want to see what work you have done, you have to save it. If you don't want this particular work to be saved, you cannot. I mean, you're free to not save it. So let's say I'm saving it as basic plots. Right? As soon as I save this plot, I can close it. And remember, I told you if you are saying any log view, you will be able to see under this particular option, basic logs. You see, if I double click again, I will be able to see it. Now, anytime I can open, reopen, close it, do any modifications. There are many other options also. I mean, many times, let's say if I want to shade gamma ray, there are many other options of over here. You see this option, fill under the area. I will choose that, and instead of choosing a single color, I will maybe assign a palette variation of a distribution of colors. Let's say I will choose that particular option. I will choose a default palette. Let's forget about other palettes. I will get confused. You can see I assigned a variation. I assigned a palette, a color distribution to gamma ray. So pink means low value, red means high value, right? So you can also assign a palette. Palette is nothing but a distribution of colors, right? Palette is nothing but a distribution of colors. So you can keep the palette lowest value as 0, upper value as 150, depending on, like, again, how what you want to visualize and how you want to visualize. So I assigned a color range varying from 0 to 150 to gamma ray. That is, higher portions of gamma ray will be in red and lower portions of gamma ray will be in pink. Okay. At times this is visually appealing. I mean, if you want to, let's say, if you are looking at a plot from 100 and maybe, let's say, 2-3 feet behind, if you are presenting something, you might want to make your plots attractive enough so that your professors or your clients might be able to see it from a distance. So you want to, let's say, do some visualization tricks. So this is one way of doing it. You can assign a palette to a curve, so that it is visually appealing. All right. So I will save this plot. And now saving is again easy. You can press Control S. Control S is for saving anything. Here I'm saving the log view. Here I'm saving the log view layout plot. All right, guys. Good to this point. All right. So let's take a break of 2 minutes, guys. I will have some water in between. Let's take 2 to 3 minutes break. You also can have tea. I'm sure if you are all at home, you can have some tea. Take a break of 2-3 minutes, and we'll come back shortly.
Okay, so we have a small break and then we'll continue.
Hi guys, everyone back from a break. Great. How about this? I can see only one individual, Kalyani. Thank you for letting me know. Vissal, Arjun. Great. Thank you, Ali. So we start our session. Let's start where we stopped.
You can start, sir. Go ahead.
Okay. Okay. So before moving forward, you have to understand few things. Maybe I'll just cover briefly, but I would recommend everyone, to. So you have to understand the cycle of a well, the life of a well, right? So in a well, let's say if it's an onshore well, let's say you have a ground level, you will set up your rig, right? This is your rig, and you will start drilling. You will start drilling to a certain point. Once you drill to a certain point, you will you will put the casing, right? You will put the casing. Then you will drill another interval starting from this depth, right? You will drill to a certain point and again put the casing. You will drill maybe another, depending on how much deep you want to go, you will drill another interval with a different bit and you go to a deeper interval, right? So you drill a well in section by section. So these are all different sections, right? I'm sure if you are aware of these terms, it will be better. So these are all different sections, right? This is one section, this is another section, this is another section. These decisions are taken by after considering multiple factors into account. Where are my target formations? Where are my, let's say, where is my reservoir? How deep I want to go, and how much overpressure I have. Like different considerations are taken into account. All right. So now in each section, you acquire some data, which is what we are visualizing in Techlog. This is called a log data. Now you acquire this data section by section. So when you have drilled this section, you will be able to acquire data in this section as well as in the section above, right? You need to drill this section in order to acquire some data over here. So most of the times you have data section by section, right? There are usually sections of 17.5. That is, so we call the section mostly based on the bit size, which size of the bit we are using, right? We have 17.5 section, we have 12/4. These are the main sections. Most of the times you will encounter these sections in the studies. 8.5 section. This means that your bit size, the diameter of the bit is 8.5 inch. All right. So you have different sections. Now each of the sections you acquire different data types. Usually these data types are in different files. You don't have, let's say, from top to bottom, you don't have one file, right? You don't have one file from top to bottom. You have data. You do acquire data in different sections in different time space, right? So when you start doing modeling, what you want to do, you want to combine the data set, right? You want to combine, let's say you have 3 sections. You want to combine the gamma ray in section 1, section 2, and section 3. You want to combine them, right? Then only you will be able to do some interpretation. You want to create a continuous log from top to bottom, correct? So that is called log splicing. Not sure if you have heard of the term log splicing or log merging. What we are doing is we are splicing the log, we are merging the logs. Again, it's a very important operation. Whenever you start doing an interpretation, you will not be lucky enough to have a log data already spliced or merged, right? So this is called log splicing and merging. What you are doing is you are just merging all the logs together. Okay, so that you can when you plot them, you don't have to create multiple plots. When you are running a model, you have just one log from top to bottom. So in this particular case, you had all the logs from top to bottom. You had logs from 500 to 2200 meters, but that won't be the case every time. You need to do splicing, right? You need to do merging. That's again a very easy operation. That's again very smooth operation in Techlog. Let me show you how you can do it. Again, it's very easy. So you see under LQC containers. So you see these are different containers. This is a survey container. Survey is telling you the direction in which the hole has been drilled. If you are aware of this term deviation and azimuth, it tells you the orientation of the wellbore. Mismatching between the sections. So the question, sometimes there is a depth mismatch, right? Between section. So depth mismatch. So you have to understand which log you can rely more. So you see, you have to keep a consistent. You have to keep consistency, right? If you want to rely on some one measurement. So first thing there would be, you need to understand which one is correct and which one is you are going to use it for your all the operations. So let's say if you have gamma ray, if you have two different tools, maybe one data has been acquired from wireline, one data is acquired from DNM. Now there are different policies which industry follow. At times people follow DNM data to do depth mismatch corrections. So you can do corrections, right? Let's say if I have gamma ray over here, maybe I don't have any other gamma ray here, but let's say if I have two gamma rays, let's say these two gamma rays are from different tools, and this gamma ray might be something like this. You see, I'm moving it intentionally further down. You see, it might be something like this. So you need to do something called depth correction. You have to match the patterns that you observed in the correct data set. It's important to understand here I'm saying correct data set, right? You need to fix one thing first, that this gamma ray is correct and this is not. Once you know this is correct and this is not, then you can maybe do a block shift, or you can shift area to area, region to region. So that comes under lock conditioning. There are a lot of things. You see, you have shifting tools over here. Since I don't have multiple measurements, I won't be able to show you right away, but you have corrections, depth shifting corrections options in Techlog. But that is something that, see, I'm a geomechanics engineer. On top of that, I really reliant on petrophysicist. So there is another science called petrophysicist. Oil and gas sector is huge, right? So most of the times I'm dependent on them, because they have they know that particular science better than me, I would say, and they do that depth corrections prior giving that data to me. Even let's say when you acquire data in the field, you don't directly use it for modeling, right? You don't really get gamma ray directly from the tool, or you don't get directly compressional slowness directly from the tool, which you can utilize it for your modeling. It goes under some processing. It goes into some corrections, right? There are noise corrections, there are some depth corrections. So those steps are usually being taken care by the field engineers or by petrophysicist team. So most of the times, as a geomechanics expert, I just QC whether, let's say, the response of the log is proportional or not. Let's say just to demonstrate you how do I QC. So let's say over here you see density. Now density for this particular interval is high, right? Density is reading 2.6, and I see a spike in compressional 2, right? It is saying my slowness, that is the time taken by the velocity, is lower, which is logical enough. So I understand that this is a depth corrected log. Let's say if this peak would have been at a relatively different depth, then I would have been doubtful. Okay, there is something wrong in that case, and I need to do depth correction. I need to maybe shift that particular curve to a certain let's say interval, so that my data is depth corrected. We have two different deep in this log, like gamma ray. High phase. Well, see, if you have now here we are talking about 10 meters of interval. Okay. So see, first thing you have to understand, Ali, that as I was saying here, so you see, when you drill a well, you need to, so you need to understand, so you have your formation, right? This is your mother earth, you have formation, this is your formation, and you are trying to capture some response, you are trying to capture its gamma ray, you are trying to capture its density, right? So first thing that you need to understand is which data is correct. Let's say you have gamma ray from 100 meters to 500 meters, right? You have gamma ray from 100 meters to now. You have to understand, when did you acquire this gamma ray, whether it was in open hole or whether it was in cased hole, what were the conditions, which type of tool you had used, whether it was a very poor tool, whether it was a properly working tool or not. So if you have to build a confidence whether the gamma ray is correct or not, right? If this gamma ray is correct or not. Okay. Now you say that the second log that you have is, it starts from 490 meters. So you have an overlap of 10 meters, right? And it goes to 700. Now, first thing that you need to understand, if there is a depth mismatch, now, but you have very small interval to understand that. I'm not sure if it is going to be helpful. I have to check the logs because it's only 10-meter interval. I'm not sure if you will be able to take a call on that. So if I were you, based on the understanding that I have from the area, I would check first if my first gamma ray is correct or if my second gamma ray is correct. Which one was acquired in the open hole, right? Open hole, I mean, there are conditions when we acquire data in the cased hole condition, when the casing has been put in the hole and then we do the measurements. So if there is a casing downhole, your measurements might be affected. So usually people rely on the first acquired data, then you rely on the second acquired data. So I would prefer to keep this log as it is, and we'll just splice it, with this particular gamma ray starting from 500. But again, as I see, this depends from case to case. Without looking at the data, it is very difficult to tell you. All right. So you have to develop some confidence. I mean, that's the bottom line. You cannot take a call just like that. You have to develop confidence on the acquisition that you have. All right. Moving ahead. Okay, great. So what I'm going to now is maybe I'll show you how do you splice the data. However, in this particular class, I'm not supposed to, I mean, it's not required because I already have the data from top to bottom. You can see I have the data already with me, but I will show you anyhow. Let's say, imagine that you have this gamma ray. Maybe I will, so if you want to break a log into two different, if you want to break a log, that also you can do. You see there is an option of split variables. So I will choose a random depth. I will split this particular log into two. Why I'm doing it? I just want to show you that if you have two logs, so you see if now I have two gamma rays, one gamma ray starts from 500. It goes to a depth of 134 meters. The second gamma ray starts from 1140, and it goes to a deep depth of 2207. All right. If I want to splice these two curves, there are again multiple ways. See, Techlog is vast. There are multiple ways. If you just want to do this exercise, select the first curve, select the second curve, right click and merge. You can see I have successfully merged the curve. As soon as I select the curve, it will be highlighted in red, right? So splicing a log is again very easy in Techlog. This is one way. This is one of the many ways I'm showing you. This is how you splice the data. And what was the preference? I chose the first log first, then I chose the second log. So in this, the algorithm will ensure that my first log is taken priority over the second. So wherever first is missing, there only I will take the second. Okay. So that's how you splice it. You see, this is my splice log, and I can maybe then save this, by giving a suitable name. Maybe gamma ray splice, let's say. Yeah, nomenclature also varies from country to country, client to client, individual to individual. So you see, I have now gamma ray of the name SPLC. This is the spliced gamma ray that I created just in front of you, right? Clear how guys, how do you splice the data? There are other tools also. I'm sure you will be covered in Techlog fundamentals. You have something called variable splicing tool, right? If you have multiple variables that you want to splice, if you have multiple files you want to splice, you can use this variable splice tool. If you want to splice only one log, you can do it the way I showed it to you, right? And there are other ways also you can splice it. I will not go into details because it will confuse you, and we will depart from the topic of geomechanics, which is our point of interest here. All right, so is it clear, guys? Shall we move ahead? Shall we move ahead to the geomechanics concept and the modeling part? We haven't covered anything on that front yet. We were just talking about Techlog fundamentals, visualization, user interface, right? Okay, okay. All right, so let me make you understand another important concept. So in software, see, you need to define the trajectory of the wellbore. The wellbore can be of this shape, right? The wellbore can be vertical. Not, sorry, this is not, doesn't look like a vertical well. Let's say this is a vertical well that you have drilled, and maybe you have a deviated well that you have drilled. Now on a deviated well, you require measure depth, you require azimuth, in which direction. Let's say if this is north, this is east, southwest, north, south, east, west, right? So you need to define which direction you are drilling. This is the top view. You need to define how much deviation the well is taking. So this is called a survey data set. Okay. It essentially has measure depth, azimuth, and inclination. Okay. It has these three curves. So you can measure the trajectory of the wellbore, if it's a deviated well or it's a vertical well. And this is predefined. And usually before drilling a well, it is known that which type of well we want to drill. But we always measure the actual profile we are drilling. Why it is required, as I said, when you drill a deviated well, the stress state will change a lot. And in addition to that, the correlation between measure depth. See, there is one thing called measure depth. This is there is something called TVD, true vertical depth. Not sure if you are aware of these terms, guys. Measure depth, TVD, TVDSS. Right? There are different terms. So these are nothing but references. So if I say that my bulk density is 2.6 gram per cc, so you should ask me which reference, at what depth. Now this depth can be measure depth, this depth can be a true vertical depth, this depth can be true vertical depth from subsea. Do you understand different references? Subsea, KB, do you guys understand the difference between them? Okay, okay. So that is very important. So see, so we need to make our software understand. Very first thing is what is the trajectory of the well. If it's a deviated well or a vertical well, we need to make software understand before doing our any modeling. Now, what is the benefit of it? Because that way, software will understand that the relationship between measure depth, TVD, measure depth, and TVDSS or TVD or TVDSS, whatever, whichever reference we choose. Right? As of now, we haven't assigned, or we haven't told our software whether it's a vertical well or deviated well, right? So for that, we have survey data set. Survey data set, you see, is that is a measure depth, deviation, and azimuth, right? These are the three different logs that we require to define the trajectory of a well. Now what we are going to create is, we'll go to data. we'll go to references and coordinates. Okay. And we will create something called TVD computation. Now, why it is required? See here, by this step, which I'm showing you, we are going to tell software, this is the deviation of the well, this is the azimuth of the well, and this is the measure depth of the well, right? This way, software will understand the trajectory and relationship among different references. So, I'm just assigning now the relevant variables required by the workflow. You see, I need measure depth. So this is the window. This is a window that got created when I selected under reference and coordinates TVD computation. I need to assign measure depth. I need to assign hole depth and hole azimuth. Once I do that, I can click on create. Now software is asking me drag and drop the data set where you have measure depth, you have deviation and azimuth. So I know that these are present in survey data set, right? I know that this is present in the survey data set. I'm just going to drag and drop over here. It has now automatically picked up the variables. It has now picked up the variables. Now here we need to also define if it's a onshore well or an offshore well. So because in an onshore well you have ground level, the drilling will start from the ground level. If it's an offshore well, the drilling will start from the seabed, right? Both the cases things will be different. Since it's an onshore well, I'm choosing it an onshore well, right? I'm going to keep this option to deeper depth. So you all saw that, right? Our well was drilled to a depth of 7280 feet. Now 7280 feet will be approximately 2 to, so if you calculate the feet to meter, it will be 2218 meters, right? So I'm extended this computation beyond to the last depth, beyond 2200. Maybe let's keep it around 2300 meters. All right. Because I want to ensure that I have data beyond the last available data set. I'm just giving a random depth of 2300 and I'll click on create. Okay. Very simple, simple exercise. Once I do that, you see now I have two files, two containers created. One is index, the other is the well path. Okay. The first is the index and the other one is the well path. Now both these data sets have their own importance. It will be clear to you as we move ahead. Well path is nothing but telling you the trajectory of the well. Okay, well path is nothing but it's telling you the trajectory of the well. You can visualize which direction our well has been drilled, and it has its own usages, no doubt. And but it is also useful to make software understand how measure depth, TVD and TVDSS are related. Okay, so that when you do any interpretation where TVD is required instead of measure depth, you don't need to do any manual intervention. Software will understand on its own. Okay, so this is a one-time step. This is a one-time step that we always follow. All right. And this is the very first step, I guess, every software requires. You need to load the survey data set for that particular well. All right. You need to make software understand. You need to make the software understand the survey file. So if you want to check the survey again, you go to data editor. This again a window will create. I just drag and drop survey data set. Here I can see different values. You can see the survey starts from 1709 feet. This is in feet, right? And it goes to a depth of 70 to 80 feet. And meters, it will be around 2200, right? Which we calculated. The deviation is not much. It is below 1 degree, especially in the interval. It's nearly a vertical well. It doesn't have a much deviation. However, instead of just for the sake of, let's say, telling you how do you do it, I have shown you how to create an index and Techlog well path. So Techlog well path, one well. So let's say when you are planning a well, right? When you are planning a well, you might in the planning stage you might come up with different scenarios. You might have, let's say, different proposals. You want to drill a well like this, you want to drill a well like this. So you can have different Techlog well, you can have different well paths, right? First, second, third, you can create multiple well paths. But once you finalize them, right? Once you finalize them, let's say you have finalized this particular trajectory. Now there, once you have finalized this trajectory, you want to make the software understand the relationship between measure depth. So this is the TVD, right? This is the TVD, and MD will be measured along the well path. So you want to make software understand the relationship between MD and TVD, right? For that you need the inclination of the well and the deviation of the well. Oh, sorry, azimuth of the well. Okay. Once you do that, and that is done using the concept of index. In Techlog, what you do is you create an index data set that should start from the top of the well, and it should go down below the target depth of the well, from at which the depth has, the data has been made available to you, right? Is it clear? The concept of index is clear, guys. Index is just a data set just to create a relationship between measure depth and TVDSS. And you can have one and only one index, and you can have multiple well paths, because you understand that well paths, we can require it for multiple purposes. You can, you don't have to, you can choose, Ali, you can work with MD, you can work with TVD, depending on the application you are working with. Most of the times, let's say if you are dealing with a deviated well, when you have a deviated well, ideally we should plot both measure depth as well as TVD. Why? Because a driller or whoever is going to do the operations, you need to understand the relationship between them, right? Now, when you acquire a log, you acquire it in MD, but you need to understand the TVD, because there are different implications of it. So most of the times we plot both. We also plot measure depth, we also plot TVD just next to it, right? So this is very important when you do any interpretation. Okay, so first step over here we adopted is we created something called index. We created something called Techlog Wellbore. Okay. Now I'm grouping this these two files that got created. So if you want to group, you can easily group it. You can select these two data sets. You see there is something called group. I will name it as index and maybe well path. Index and path. You see now a group has been created, just similar to what I had for calibration dataset. And I will keep my index and Techlog well path over here, because I'm not going to utilize it, these datasets in the geomechanics part directly. Software will itself understand what is the relationship between MD and TVD. Now there is one correction that here we should do it. Now, as I was explaining to you guys, let's see if it's a ground level. Now, in order to make software understand that the relationship between measure depth and the TVD, your survey should start from ground level only, right? It should not start from somewhere in between. Now, in that case, software will not be able to understand the relationship between MD and TVD in this particular interval, right? In this interval, software will not be able to understand. So that is the interval which you need to take care of, right? So see, biggest challenge in any modeling is to create a data set, to get the data set, to create the data set, to create a composite file, to have a proper data set which is from top to bottom, to do depth corrections, things like that. These are the primary tasks when you, let's say, take data set from someone. You need to do some QC, quality check of the data that you have, correct? So here, if you look at the survey data set, it starts from 1700 meters. It has a deviation and an azimuth, but it doesn't have anything from the ground level, right? So what I'm well is vertical, because we have seen that the deviation is less than 1 degree. So for all practical purposes, the well is a vertical well. And what I'm going to do is I'm going to add one row, just like an Excel sheet. I'm going to add one row. I'll add one row before, and I will add a value of 0, that is from 0 MD, the deviation is 0 and its azimuth was 0. So as soon as you start drilling the well, it was a vertical well. That's a very genuine assumption, I would say. So you see, I added a line starting from 000. All right. And as soon as I did this modification, you see the star mark. Star mark is telling you that the data is not saved. You need to save the data set. You see at the top, I'm going to click on save all the variables just to ensure that my modified data set is saved. Now, when I look at this data set, now see it is starting from 0, right? Initially it was not. And it is intentionally done for this particular data set because, you might face this challenge many times. Understood, guys, what I'm trying to tell you over here? Is it clear what I'm trying to tell you? So I'm trying to tell you different challenges that you might acquire with the practical data set. Since you are students, I'm sure you will acquire a lot of challenges. But this is one of the key challenge. At times you will have data missing in some interval, and times you have complete data. All right, so I added a line called 000, that is at 0 depth, the deviation is 0 and azimuth is 0. Now, very similar step I will do. I will create my TVD computation again, right? See, the variables are auto saved. Once you define the inputs, Techlog tries to remember what you want to define. So it has remembered my last given inputs. Very similar, what I'll do is I'll give the survey data set as an input, but this time, see, it will start from 0. It will not start from 1700 feet. Rest, everything I will keep as it is, and I will keep, instead of 2218, I will keep a depth of 2250. I'm choosing a relatively deeper depth because I want my survey to cover, my index to cover the entire interval of the well. Okay. So you see, as soon as I did that, my index got updated, and there was another Techlog well path got created. As I said, you can have multiple well paths, but you will have only one index. All right. Understood, guys? I deleted the last well path because I don't require it for any purpose. So this index, now see, this index will start from 0. If I plot the data from in a log view, you will see that it starts from 0. See, it starts from 0. Initially, it was not, right? Okay. So we have covered a very important concept of importing, loading the survey data set and defining the relationship between TVD and MD by means of creating an index. Okay. Now what we'll do is we will open the basic log file which we created some time back, and we will plot the zonations. As you know that in oil and gas sector, we have different formation names, right? At the bottom, you see different formation names. So these are the local formation names. I am assigning a color to them. And I can plot these names on the log view that I had prepared in front of you all. So Belfast, see, again, very famous formation. Vara is a very famous formation. Parate. So these are the local names. You don't need to worry about them. You don't need to remember them. So you just need to understand that this particular formation, let's say Belfast, it was deposited in a particular time period, and it will have a certain age, geological age. Okay. Right, and usually in different countries, people tend to assign different names to those formations. I'm sure in Algeria, in your case, you will have, you will have different names in your areas. You might, if you see some data set, you will have different names. If you see the published literature, you will have different names. In India, we have different names to the formation. We have given different names. Okay, so the nomenclature is quite local in nature, but the important aspect will be its age. Age is universal, right? A formation deposited in Miocene will always be in Miocene. Right? You won't be able to change that thing. Okay, so you can plot the name of the formations corresponding to the different logs, right? That's again something that is very useful because for a driller or a reservoir engineer, they want to understand what is happening in Belfast, what is happening in Vara formations, right? They want to understand the behavior of the formation. That's what it matters all the time. Okay. So that's how you plot the formation tops. So you see, I had the formation tops with me. If you want to visualize the formation tops values, these are nothing, just the depths, the start point of this particular formation and the end depth. Okay, start and the end, start and end. Okay. Yes, you can do subzonations also. You can do subzonations also. We can go to any extent you want. So so let's say I'm trying to avoid because those are fundamentals. I mean, if you go there, so you see, I can change the zonation thickness. There are tools in Techlog which can help you to. These are edit zone options. You can divide the zone. You can create additional zone. You can change the thickness. Let's say, right? There are multiple options with you there. I will not use this. So I'm not going to do that. We'll disturb this data set. How do you display formation tops in the log view? Okay, I will repeat it. I will repeat again. So you see this zonation window. Remember, I told you about the zonation window. This is the window where the zonations that you will load in the data set. So first thing you should ask me that how did I get this formation tops, right? So these formation tops, that is the name of the zones, they are picked by a geologist. They are picked by operation geologist on the site, or those who acquire the data and do the interpretation. You can also pick it, even I can also pick it. No, that's not an issue. But important thing here is you need to understand the initial point, the starting point of that particular formation. Let's say Belfast starts from 5685 feet. Okay, you need to prepare this data set where one depth will tell you about the initial point, starting point of the particular formation, and the other depth, subsequent depth, tells you the starting point of the next formation, and in between it will extrapolate. All right, so once you create this data set called formation tops, and if you want to display that formation tops on basic logs, what you can do is, so let's say if I don't have them here, you go to your zonation doc window. In the zonation doc window, you will be able to see the formation tops, the one data set that you have loaded, and you will be able to see all the names, right? And you can just press Control A. Control A, that is, I selected all the names, all the formations, and I want to display them. You see, by default, it displayed different colors are associated with different formations. And if you want to display the names, right click and you see this option, insert an empty zonation track. You see, so this is a zonation track, just like in log track, you have zonation track, which you can use it to display. Now you see it's a vertically, I mean, the names are vertical, and if I want to make them horizontal, you go to properties and choose this option. I can change the thickness of the track so that the names are clearly visible. So this is how you display the formation tops in a log view. Okay. You can pick or you can modify the formation tops. You have multiple tools are there. See, I can change the thickness. You can do a lot of modifications there. Not an issue. Okay. Understood to this point, guys? Understood things related with the formation tops, log view. All right. Nice. Any doubts so far? No doubts, right?
No questions, so you can go on.
Okay. All right. So now let's start the geomechanics section. So until this point, see, I covered a lot of fundamentals of Techlog. So as a young engineer, I would recommend you to practice. See if you are able to, if you have a license in your college, if it is there, it will be great. That way you will be able to practice, because practice is the only thing that is going to make you perfect. If you don't practice these steps, you won't be able to understand what I'm trying to convey. Okay. Techlog is a huge software. I mean, a lot of variables, a lot of steps are there. But depending upon the domain you are working in, depending upon the application you are working in, you can narrow down the applications. Right here, we are mainly focused on geomechanics. That's why I covered some of the very initial aspects of Techlog which are required and which I'll be using going forward. Okay. Okay. So let's let's talk about what do we do in geomechanics. So as of now, we have understood, guys, we have understood as of now that in geomechanics, I mean, we have understood that geomechanics has wide variety of applications. Okay, that's something that we have understood. But exactly what do we do in geomechanics? What do we need to understand the rock behavior? What do we need to, what type of model we are going to prepare? Right, that must be your primary question. Okay. So in order to understand what do we do in geomechanics, I'm showing up this slide. You see, on the first thing that I'm showing is the lithostratigraphy, that is sand shale sequence. The orange color is sand. The wood color is the shale. Assume that it is a shale. So this is a sand shale sequence that I'm showing. Right, sand shale sequence that I'm showing. Now, these different sequence, different layers of the rock will have different properties. In geomechanics, we try to understand different rock properties. These properties are basically categorized into different classes. The first is we'll talk about the elastic properties. If you have gone through, let's say, the stress strain curves in your school life or college life, if you have done some experiments, you will be aware of these terms. These are very commonly used terms. So elastic properties consist of mainly Young's modulus and Poisson's ratio. They tell you about the elastic behavior of the rock. So you see this blue color curve, it's a cartoon only, right? So this cartoon is telling you the behavior of different lithophases. Orange has lower Poisson's ratio and the wood color has a higher Poisson's ratio. Now, I'm not going to define here Poisson's ratio. Are you guys clear? Like, what does a Poisson's ratio mean? I'm not sure if it's a easy word for you all. It's clear, right? Okay, cool. So Poisson's ratio is also called as the fattability parameter, right? It tells you how much amount of lateral strains, how much your rock is going to spread out. Yes, how much your rock is going to spread out when you apply a certain stress, right? So shales in general will have relatively higher Poisson's ratio. That's why you see, blue color curve over here corresponding to shales is relatively high as compared to orange color curve. Here it is relatively low. So in geomechanics, we try to understand the elastic properties of the rock. That is, we try to understand the Young's modulus. We try to understand the Poisson's ratio. Okay. Then we try to understand the strength of the rock. Okay. The strength will consist of uniaxial compressive strength. Again, I'm not sure if it's a known term to you all. UCS, that's the acronym that we use. It is uniaxial compressive strength. If you have seen the stress strain curve, that is the peak load a rock can bear before failing. Okay, so that's something called UCS, or in short, rock strength. Okay, so different layers will have different rock strength. You can see there is red color curve is varying in different lithophases. Okay, different layers. Then you have something called friction angle, which is in green. Again, it's a cartoon. The actual log will not look like it. It's a friction angle curve, right? That is something that we want to understand. So in geomechanics, the two important aspects would be to understand the elastic as well as the strength properties of the rock. This will help us in understand how strong my rock are, how much elastic behavior they are going to show when I apply a certain stress on them. Okay. So these are important 4 properties that we are going to compute in Techlog. Apart from that, you also want to understand the in situ stresses. Okay. Now, can somebody tell me how rocks are different from the metals? Can somebody tell me in one line how rocks are different from metals? It's a question to everyone. Please tell me how rocks are different from metals. How rocks are different from metals. What will be your answer, guys? Anyone?
I think we have
Metals,
an answer, sir.
metals can be malleable, rocks are brittle. Okay, any other thing? What is the very basic thing different for rocks? Any other attempt? Anyone? See, the answer is there on this slide. I'm just trying to pinpoint. I'm just trying to understand if you are understanding the point. What do you think? What is the difference? Any other try? No. Any other try? Think of very basic nature, guys. Think of very basic nature. That's fine. All these are applications. So see, let me tell you the answer. Rocks are porous, guys. Isn't it? Rocks have porosity. Metals, let's say if you are creating a steel structure, if you are, let's say, any civil engineering job, you are trying to use a steel structure, you're not going to make it porous, isn't it? You will make it solid so that its strength is higher. It doesn't have any pore space in between the grains. Am I correct? The rocks are porous, right? That's why in rocks we talk about the porosity. Is it logical, guys? Is it logical? Great. Because see, elasticity of rocks, it can vary a lot. The strength of the rock can vary a lot. At times, rocks can have higher strength as comparison with metals. That is not an issue. That is not a differentiation factor. That will not differentiate rock from metals. The main feature of rocks that differentiates it from metals is its porosity. Okay, now because of this porous nature of rocks, the rocks will have something called pore pressure. Its pores are fluid. Its pores are filled with fluid, and this fluid consists of some pressure, which we call it as pore pressure. Okay, pore pressure is a thing that you don't have it in metals, right? And pore pressure is only present because of the pore space. If there is no pore space, there won't be any fluid, there won't be any pore pressure. Okay, and that's where you see there will be a lot of difference in civil engineering domains as well as in rock mechanics or in geomechanics, let's say. So geomechanics, we consider the effect of pore pressure, and in civil engineering, you won't see that metals, we don't consider any internal pressure in them. So rocks have pores and pores have fluids. Fluids have some pressure, which we call it as pore pressure. Okay. Now there are some other things like the rocks that are there down the earth, to a deeper, let's say 2 kilometers down the earth, they are under a state of stress. There are overlying rocks on top of that. There are elements just around that particular rock which are continuously compressing it. So that's why it is said that a rock is always under a rock is always under a state of compression, because it is being compressed from top as well as from the sides. Okay, why it is being compressed? There are various reasons, but that drives us to a concept of principal stresses, principal in situ stresses. Okay. So in 1D mechanical earth model, we talk about three principal stresses, sigma 1, sigma 2, and sigma 3. I'm not sure if you have heard of these names, but there are three principal stresses: maximum principal stress, intermediate principal stress, and minimum principal stress. Okay. And that is what we will try to estimate in the field of geomechanics. And other property that we have is the stress direction. We want to understand the direction of the stress. Guys, give me a minute. I'm just getting. Sorry guys for the interruption. So yeah, I was saying that in geomechanics, we try to understand the elastic properties, strength properties. In addition to that, we will also estimate pore pressure and stresses. Now, why we are going to do that? Why it is important? Let's try to understand that particular part. Let me bring my whiteboard. So how many of you have heard or how many of you have seen the stress strain curve? Stress strain curve. I'm sorry, I don't have a pen with me. I'm just typing it with my mouse. So have you heard of, have you seen the stress strain curve? Right. Now in a stress strain curve, what do we try to do? So we have a rock sample, let's say. We have a rock sample, right? We apply some stress in the lab. We apply sigma 1, right? And we measure how much this rock is going to compress under this particular sigma 1, how it is going to behave, right? That is the whole objective. So what we do is we create a plot. On y-axis we have sigma, on x-axis we have strain represented by epsilon, right? And then you plot a curve like this. Stress is proportional to strain to a certain point, and then it starts deviating, goes to a top point where rock will be unable to bear any more further stress, right? And then there will be a lot of fractures getting created, a failure plane will be created, and this rock will fail. This rock part will be broken after this point, right? This is the peak load. This is the peak stress the rock can bear. Have you all seen this curve? I'm not sure if it's covered. Everyone is covered, right? Because we'll be talking about it a lot. And that's what we're trying to do in geomechanics, right? That's what we're trying to do. So in geomechanic model, we prepare something called mechanical earth model, as you saw in the last slide. We are trying to prepare a mechanical earth model, MEM, we call it an MEM, mechanical earth model. What you saw, we are trying to compute Young's modulus. Can anybody tell me what is Young's modulus in this curve? Can anybody tell me what is Young's modulus in this curve? The slope, right? The slope. Very correct. So we want to measure Young's modulus. That is nothing but the slope, that is change in stress divided by change in stress strain in the elastic region. Remember, we do it in the elastic region, right? The slope of the stress strain curve in the elastic region where the Hooke's law is valid, right? So we measure this slope. This slope is nothing but the Young's modulus. If I want to measure Poisson's ratio, you can measure something called radial stress or radial strain. If you have the radial strain, you can again measure Poisson's ratio, correct? very similar to Young's modulus because you know the longitudinal strain. If you measure the lateral strain, you can measure longitudinal strain, then you can get Poisson's ratio, right? Same goes for mechanical earth model. I told you we will try to get an understanding of Young's modulus, Poisson's ratio. Then I told you we will try to get an understanding of strength parameters, which is UCS. UCS is nothing but the peak load, right? Peak load a rock can bear under no confinement. Okay. This is the peak load. This is the maximum value of stress a rock can bear given that there is no confinement. Okay. So we'll estimate rock strength, UCS. We'll understand friction angle. So you might have, in your higher school, you might have heard the coefficient of friction, right? Represented by mu. So it's a surface property, right? That's something that we'll try to understand in geomechanics. In addition to that, we will also try to understand something called tensile strength. As the name indicates, tensile strength is nothing but, let's say if you have a rock, let's say if this is a rock. Now, if you are pulling this rock apart, what is the stress at which this rock will fail? Okay, this will be the tensile strength. Let's say if you are pulling this rock with force F, right? Certain value of force, this rock breaks. Now this damage or this failure will be in tension. Here the failure was in compression, right? We were compressing the rock, but here we are extending, we are stretching the rock. Then the rock will fail in tension. Okay, both are two different phenomena. So we will get a understanding of friction angle, we will get understanding of UCS, we will get an understanding of tensile strength. Now, in addition to these rock properties, which you can see on this slide, what are the other things? So here, these are going to help you in understand how much stress a rock can bear, right? But before even going there, you need to understand how much stress is being applied on the rock, correct? You need to understand how much stress is being applied on the rock before doing anything. Okay, so that's why I said after elastic and strength properties, we will try to understand principal stresses. Usually these principal stresses are represented by sigma 1, sigma 2 and sigma 3. If you look at the principal stress matrix, it will be 3x3 matrix. I'm not sure if you have gone through the theory, guys. It's a 3x3 matrix. You have three principal stresses, right? Do you know these terms, principal stresses, guys? Sure, you have learned in your theory classes, right? Okay, great. So we will try to estimate values of sigma 1 and sigma 2 and sigma 3. Why we want to do that? Because then only we will be able to understand with the given value of sigma 1, sigma and sigma 3 and rock strength, whether our rock is going to fail or not, whether this rock is going to deform or not. You understand the logic, guys? So mechanical earth model, we will estimate stresses as well as elastic and strength properties of the rock. That's all the mechanical earth model is all about. We will try to understand these properties, then only we can understand whether our rock is going to fail or not, whether the rock is going to deform or not. Correct? You understand the logic behind what we'll try to do in the coming time? Clear everyone? And what do we call mechanical earth model? So I'm summarizing the overall process again for you all. So you have, so there in one dimensional, in 1D model, we assume that our stresses are, so there are three principal stresses in 1D. We assume that one of the principal stresses is vertical stress represented by sigma V or SV. The other principal stresses are S small h and F capital H, sigma capital H and sigma small h. These are the two horizontal stresses. You have the orientation of sigma small h Now since these are three principal stresses, they are orthogonal to each other, right? So we just need to know the orientation of one of the horizontal stress. We will automatically know that the other is 90 degree to that. We also saw that we need to understand mechanical properties of the rock. That is friction angle, tensile strength, cohesion or UCS, Poisson's ratio, Young's modulus. Okay. And the last thing, but again, a very important part, which is the pore pressure. We want to understand the pore pressure of the rock, how it is varying with depth. Because we know that it is going to play a vital role in the area of geomechanics. So that is what segregates rocks from metals. Okay. Once you prepare this mechanical art model, then only you can apply it to different applications. There are the applications, remember, we discussed in the first slide, then only you can apply it to different applications, right? Whether it be mudbed design, casing design, and things like that. But in order to do that, you need to prepare a mechanical art model. You need to have an understanding of rock strength. You need to have an understanding of plastic properties, stresses, and etc. Okay. Now, in the stress strain curve, it is worth mentioning that the stress strain curve, you see, it is for a particular depth. You make this plot for a particular depth, right? Now, in a wellbore, you have an interval of maybe 4 kilometers, right? You have an interval of 4 kilometers. So you will do this analysis at each of the depths. You won't do it. I mean, software will do it. You don't have to worry about it. But yeah, that's where you require technology, as I was saying, right? You cannot do depth by depth interpretation. So each of the depths, you are going to understand with the given stresses, whether your rock is going to fail or not, whether how much strains you are going to develop, right? You will try to do all those analysis. And you will be doing it from top to bottom, wherever data is available to you. Okay. Okay. Hope I was clear, guys. I'm not covering much of a theory since it's a software session. I don't know if it's boring, but geomechanics is a very interesting subject. I would recommend you to go through some theory of it. And if you have any doubts, you can always come up, with those doubts in the next session. Because there are good amount of details in the field of geomechanics. I'm just trying to give you a broad overview what we are going to tackle in software. Okay. All right. So let's talk about one of the principal stresses. Let's say this is the ground level. So let's say this is the ground level. This is your rig, and maybe let's say there's a rock piece over here. There is a rock piece over here. Now, see this rock piece, let's say it's at a depth of 2 kilometers. It's at a depth of 2 kilometers. Right? Now, on this particular rock element, there will be a stress on its top surface, correct? On this particular rock element, there will be a stress on its top surface. That is nothing but your overburden stress at this particular depth. Now, what is the reason for this stress that will act on this particular surface? Because on this particular elements, on top of it, you have another element, right? Above this element, you have another element. On top of this element, you have another one. You have another one, right? Likewise, you have many elements, small elements, extending until to the ground level. These are the overlying rocks, right? And this rock, let's say when this rock is placed above another rock, it will apply some gravitational force, right? It will apply some force on top of the rock on which it is lying. Now, when these two rocks are placed on top of another rock, now these two will apply a certain force on this particular rock piece, correct? So this is the concept behind overburden stress. So at a given depth, at a given depth, you can estimate the stress or the pressure or the force applied by the overlying rock mass. That's why it is called overburden stress or the vertical stress. Okay, vertical stress. And we also see you can easily estimate vertical stress by just multiplying the mass of that particular element by the gravity. Now gravity is a constant. Mass, you can estimate density into volume, right? So volume is again constant because we are considering a point element. Density is something that you can measure, right? We can measure density in the wellbore, in the violin tools. Understood? That's why in literature you will see that the overburden stress is expressed as rho g delta h, the integral of rho g delta h. Okay, starting from 0 to a depth of d. So you have to integrate the force applied by these individual elements and combine them to a given point of interest. Okay, is it clear, guys? The concept of overburden stress is clear. I'm going fast, I know, but I'm assuming that you know at least something about geomechanics. Great. So in geomechanics, the first step that we will do is estimate the overburden stress. So the first thing that we are going to do is estimate the overburden stress. Okay. So you see under geomechanics, the first step is overburden stress. Okay. So as I was saying, the critical input for estimation of overburden stress is the bulk density, right? The density law. So that's why the workflow is asking for the input of bulk density. I'll go click on create. Now, as soon as I chose under overburden stress, I chose the first method. I do have the option of choosing other methods. Okay, I will tell you the reason why I chose this method later. Assume that this is the only method as of now, and the name of the method is extrapolation method. Now, this window pops up, right? This window is called a workflow manager. Just get used to this term. This window is called a workflow manager. This term is related with Techlog. And this workflow manager, yes.
Someone is asking if you can repeat the last procedure.
You mean the overburden stress?
Yes.
Okay, so let's say if I have three blocks, one on top of other.
Sir, I think just how to proceed in Techlog, not the theory.
Okay. Okay.
Thanks.
Okay.
Thank you.
So in geomechanics, I will close this window. Go to geomechanics, overburden stress, and choose the first method, extrapolation. Maybe when you start your own Techlog in your own machine, you might not have any variable assigned under bulk density. Okay. So as I said, in order to estimate overburden stress, you need bulk density as input. So I just gave bulk density as input over here. Then I clicked on create. This window came up, right? This window is again movable. It's called workflow manager. And on the top, a name is written. Now this, as the name suggests, it manages your workflows. Currently, we have just one workflow of overburden stress. That's why under workflow, you have extrapolation. Extrapolation is a method to estimate overburden stress. Okay. And what this workflow is asking, it is saying, please drop your data set. Now it is asking for the data set where you have the overburden stress. Okay. So you see, I just took this data set, LQC data set, and drag and drop over here. Okay. As soon as you do that, you see it has picked up the well name, it has picked up the data set name, and it has picked up the input log. What is the name of the input log? RHOZ. Remember from the log view, we know that RHOZ is the density, right? Bulk density. So that is the log it has picked up. And if you go to the parameters, so there are different parameters here, you see. there are different parameters which we need to adjust in order to estimate the overburden stress. Okay, let's keep these parameters as it is, and let's check out what are the default results. What are the default results? Let's check it out. Okay, so now if you want to run this workflow, let's say if you want to run a command, from where you can run it, do you see this option of play button on the top under method settings? So you can choose which in which format you want to run the workflow. Currently I am choosing the display option. It only means that I am going to display the results. Okay, and I will just run this play option. As soon as I press the run option, you see a window pop up, and I have with me this particular layout. The first track is the density, extrapolated density. The second track is the vertical stress, S vertical stress in kilopascals. The third track is OBMW, that is overburden stress in equivalent mud weight. Okay, overburden stress equivalent mud weight. EXT is showing you that this is from extrapolation method. Okay, and after that you have the actual density curve and you have the extrapolated density curve. Now let me explain it to you what we are trying to do here. I'm just going back again to my notebook. So you see, as I said, you have ground level, but you have density starting from some depth which is not from zero. We have seen that we need density from zero in order to understand the overburden stress, right? Because we are going to integrate from the top. Now, since we don't have anything in this particular area, what we are doing is we are extrapolating the data. We are extrapolating this, let's say this is the actual density curve. We are extrapolating in a way following this particular trend. Understood? What we are trying to do in extrapolation method. We don't have data in the shallow interval. We are trying to extrapolate and create a synthetic curve. In rest part, we are going to keep our data as it is. Okay. So you see this red color curve is the extrapolated curve. We were not having density in the shallow interval. This red color curve is not present in the shallow interval, but we have extrapolated it. Okay. Once we have the density in the shallow interval, now it's a simple calculation. You just need to integrate, right? You need to integrate density over depth, and you can understand the overburden stress. Now, the software by default, it will tell you the variation of overburden stress in absolute pressures, that is kilopascals, as well as in gram per cc, that is equivalent mud weight. Okay. Then what about the parameters that we were seeing over here? These parameters are nothing but these dot points. So you see the extrapolation. Now there are some control points in extrapolation which user can modify. Let me turn on this automatic launch option. This option is called automatic launch. Now you can modify this depth. You can modify these control points. You can see as I am modifying my control points, my density is getting changed in that shallow interval. As my density is getting changed, my overburden stress is also getting changed. Okay. Understood? Clear, guys? Is it? Are you guys able to follow me? What I'm trying to say here? Is it clear, guys? Is it clear? Is it clear? Great. So that's how you estimate overburden stress. Okay. Once I finalize the parameters, once I know that this is the trend, okay, the blue color line is showing you the trend. Once I am sure of the trend, why I have to adjust the points? So, I mean, see the default. If you go with the default points, you might have a kink. I mean, let's say if you see a model like this, do you think? So let me zoom in. Why I have to adjust the point? So let's say if you go with the default parameters, you don't have density in the shallow interval, yes or no? You don't have density in the shallow interval, correct? You want to create a synthetic density, correct? Are you able to understand what I'm trying to say here? So let's say you have density here. Let's say this black color curve is a density. Okay, 1.65 to 2.65, let's say. Now, if you don't have density in the shallow interval, what you are going to do? If you go with the default parameters, you might obtain a synthetic curve like this, right? Now, this will be your final curve. Now this kink, but how do you explain this kink? You cannot explain, like you expect that with the increase in depth, your density of the rock is going to increase gradually, correct? So you will expect a smooth transition. That's why we are trying to change these parameters. That's why we are trying to change these control points. Okay. So if I choose random control points, you will see there is a kink in the shallow part. This is the final density curve which is being obtained, density underscore combined underscore extrapolated. Okay. And by changing this point, I'm just changing the trend of this blue line. You see this blue line is getting changed. And this blue line is getting spliced on the first track. So at the end of day, what is my objective? My objective is to integrate or to create a composite density, a density curve which starts from the top. And I'm trying to identify a trend using these control points by looking at my actual data and identifying a trend. Once I know the density from ground zero, then it's simple integration. You just need to integrate density over depth to get overburden stress. Okay, so you can change the color of the different logs. That's okay. So you can see I am plotting vertical stress, which is presented by S vertical. And there's another stress, same stress expressed in equivalent mud weight in gram per cc. Are you guys aware of this equation? Let me type it down. I'm not sure if you are aware of this equation. Maybe let me type it down on the slide set. So are you guys aware of this equation? Pressure in PSI is equals to 0.052 into mud weight in ppg into depth, that is TVD in feet. Have you guys seen this equation before? Can anybody confirm? Have you guys seen this equation before? It's quite simple equation. We are just trying to convert absolute pressures in mud weight equivalent. Have you guys seen this equation? Anybody? I guess it's the very first equation that you learn in your. Okay. So you see pressure can be expressed in PSI. You can express the same pressure in mud weight equivalent in density, in the form of a density. Let's say if I tell you that there is a pressure of 6,000 psi, okay. If I tell you that there is a pressure of 6,000 psi at let's say maybe 6,000 feet, okay. Right. So this thing I can also express in terms of mud weight, that is in ppg, pounds per gallon. What will can you all do the computation for me? Let's say the pressure is 6,000 psi, my depth is 6,000 feet, so this will become 1, and it will be 1 divided by 0.052, right? So this is 19.23 ppg, correct? That means my equivalent mud weight is 19.23 ppg. So you can express 6,000 psi at 6,000 feet in terms of ppg, that is pounds per gallon. You are trying to understand the logic, right? Why it is important, guys? Why it is important? Because see, when you are drilling a well, you have to decide the density of the mud. There you won't be able to measure the absolute pressures. You will only be able to modify the density of the mud that you are going to use. Because at the end of the day, pressure, absolute pressure, it varies with depth. But density, you can keep it constant, right? Okay, let's do an exercise for you all. You have to solve this question, and it's a break and exercise two both. Let me give you a question. Let's say there is a beaker. Let's say there is a beaker. It's 2000 meters deep. Let's say this is a beaker. It is 2000 meters deep, and it is filled with water. Okay, it is filled with water. Okay, understood? If it is filled with water. Now I want you all to estimate pressure at 1500 meters and at 2000 meter for me. This is an exercise for you all. I want all of you to do that, and it's a 10 minutes break. Once I come back from the break, I need answer from all of you. Okay.
Sir, I think we have some answers. Sir, can you hear me?
So guys, is this a easy exercise for you all? Are you able to understand what I'm trying to say here? It's a very easy computation. Well, everything is there in front of you. So how did you do it? What is the density of water? What is the density of water you took? Very correct. Very correct. So density of water. So water is, approximately 1 gram per cc or 8.3 to 8.5 ppg. These are some. These are very same units. Different units. That's why different values. So either you could have taken 8.3 to 8.5 ppg because this equation is in ppg. You can take any value between 8.3 to 8.5. You know the depth, that is 1500 meters. Meter you have to convert it to feet, right? And you have to multiply. So let me see what will be the result. So at 1500 meters, 1500 you will multiply it by 3.2808. That will give you the value in feet. You will multiply it by 8.3. That is going to give you the other factor and multiply it by 0.052. So 2123 is the pressure in psi at 1500 meters. Okay, 2123. I see that many of you have achieved very similar expressions. I see some of you have wrong calculations. 75 psi. I see one value. 2842 will be correct. 21 that most of you have obtained the correct results. But it's a very easy exercise, right? It's a very easy exercise. It's a very easy exercise, and you have to understand that you can. All I'm trying to express by this exercise is that you can convert your pressures in psi to equivalent mud weight, that is mud weight in ppg. Now this conversion only requires depth. You just need to know the depth, at which depth you want to do this conversion, and you can do the conversion. Okay. If I go to Techlog again, you see I have vertical stress as vertical. It's in kilopascals. It is not in psi. You see it is in kilopascals, and I have converted kilopascals to gram per cc. I mean, software has automatically converted it. It has converted vertical stress in kilopascal to gram per cc by default, because most of the times we require both the values for our own understanding. Okay, is this clear, guys? Is this clear, the concept of overburden stress? How do you estimate it? What is the importance of density log? So I guess it is clear. Okay. Now you see I ran the workflow in display mode. Now I will just go to save option and I will run it one more time. As soon as I run it in save mode, you see these outputs are saved in my project browser. Under well A, these outputs are saved. Right? What all outputs are saved? Extrapolated density, which I have created, combination of the extrapolated density and the original density. You have the overburden stress in mud weight equivalent. You have the overburden stress in kilopascals. Okay. If you don't want the stress in kilopascals, you can convert it to psi by simply right click and choose the relevant unit. I can convert it to psi. Now my overburden stress will be in psi. If I drag and drop now, let's say if I want to convert it to psi, you can see it's in psi now. I can change the units and plot it in psi. You see my stress at overburden stress at a depth of, let's say, 2 kilometers is around 6000 psi. Okay, and corresponding equivalent mud weight is 2.2 gram per cc. All right, so you can convert even gram per cc to ppg. That is also very easy. Select a particular curve and choose the required unit system that you want. It's in ppg now. You see at a depth of 2 kilometers, my ppg equivalent mud weight equivalent is 18.5. Well, we have, see, the code is there in C# in Techlog. Python, we usually prepare some other, let's say, things which are not a part of Techlog. So this is a standard workflow, and that the code is there in the background in a different language. This is not in Python, I believe. It's in a different language, but we are using the extrapolation method. So it's an inbuilt method in Techlog. We are giving the input of density, and we are extrapolating the density in the shallow interval where we don't have the density. Once we have the combined density, we are creating overburden stress, okay, from top to bottom. It is as simple as that. Okay, Arjun, is it clear what I'm trying to say? All right, guys. We covered a lot of things today. I will give you some assignment. Uh, I will give you some assignment. Please keep a note of it. I would like you all to go through the basic logs. I want you all to understand what is gamma ray, what is density, what is neutron porosity. I want you to understand what is compressional slowness, right? I want you to understand what is shear slowness. So these are all basic logs that are required in oil and gas sector. I want you to go through the basics of them. You can just Google them. You will find a lot of resources. You can watch YouTube, any other channel, let's say, go through it. Next, I want you to go through the stress strain curve. What is its significance and how do we obtain UCS, Young's modulus, and Poisson's ratio from the stress strain curve? Okay. In laboratory language, in rock mechanics laboratory language, we call it as a uniaxial compressive strength test, UCS testing, or we have another test called triaxial testing. Right? There are different laboratory experiments that we can do on different rock samples. I want you to go through them. Okay, let me put it this way. And I would recommend you all to maybe, apart from that, you try to read something about pore pressure. Read about pore pressure. What is pore pressure? Read about it. Just give it a quick reading on any published papers. Maybe I can share a paper with you. You can go through it. Okay. So that when we start our next session, you guys are on the same page and you have some basic understanding of what we are going to model. See, if you are modeling something, you have to have some basic understanding of what we are going to do. And these are very important in geomechanics, as we have seen. Okay. And after this session, maybe I will send something to the coordinators. I will send a quiz, which you all have to give. Quiz will have certain questions, and the answers will not be known to anyone. I will confirm the answers separately, but that quiz will be circulated by your coordinator, Mr. Nabil. I guess he will circulate the quiz. I will send the quiz to him. You have to, I guess, complete it in order to obtain the certification from SP. Yes, I will keep a note of it. I will share links of open source of data, and I will see if I can send some papers to read. Okay.
Okay, thank you, sir. I think that we are at the end of the session.
Yes, Nabil. I guess it's good for today. We have covered a good stretch.
Yes, it was really a very informative session. Thank you very much. And I think that you answered all the questions during the sessions, which is really better.
All right. So Nabil, I will send you the questionnaire. Maybe you can circulate among everyone, right? So that they can attempt. And maybe we'll. So next session is scheduled on Sunday, I guess. That is on 4th
Yes,
of April.
it will be, yes, it will be on Sunday, yes.
So 4th of April, guys, I will see you again. Hope you please come prepared. I will see if I can organize a surprise quiz. It won't be a surprise quiz, but yeah, maybe another quiz next time. All right. Meanwhile, I'll give
Okay,
you
thank
some
you,
time to
sir.
go through the basics. Okay.
Thank you.
Okay.
Thank
So
you.
thank you guys. Thank you everyone for attending the session. I'll see you again. Bye bye. Take care.
Thank you.